Okay.
Okay.
Just a sec. Yes, we can start.
Good.
Eduardo,
Yeah.
if Yifang do not connect in 5 minutes, send a message to him by iPhone, by telephone. Someone, no, this is profile picture. What's that?
Huh?
My camera.
I'm trying to adjust the role from different people now, okay?
Okay.
Hi, good morning.
Morning.
Hi, Professor. Good morning.
Wake up today.
Okay.
You are not. We wait for Yifang.
Okay.
Carlos.
You see,
Carlos Garcia is raising his hand, I guess.
you see, I'm in real. At least I'm hoping.
It's cold here. Eduardo, I guess Carlos Garcia is his hand up.
Yeah,
I
yes.
guess.
A lot of people is entering now, so I'm trying to catch up.
Okay.
Harvey,
Yes.
perhaps it will be good if you send a message to Yifang
Okay.
saying that we are waiting for him.
Okay.
Perhaps with this change of time, perhaps he does some mistake. I don't know.
Well, we don't know because his talk is scheduled at 10, but I will send him a message.
Yeah.
Okay. Send a message saying that we wait for him. And when he will be logged, I start for a short, or if you want to say some word for him, I pass after to open, I call you because the moderator today it will be Juvan.
Okay.
And but if you want to say some good morning or a little bit more to him, we give you the opportunity.
Okay. Good.
Okay, Juvan.
Yeah, sure.
Bom dia and good morning to everybody.
Good morning.
Good morning. Who is?
It was Carlos Garcia Canal.
Carlos. Hi,
Ah,
Carlos.
Carlito, how are you? ¿Cómo estás?
Fine, thank you. Tudo bem.
Tudo bem.
Tudo bem?
Tudo bem.
Quem que vai falar, velho? Até a hora do almoço. Esse cara não vai falar. Velho. Só às 3 horas da tarde.
Okay, I sent him a message.
Good. Thank you.
The old invitation says July 9 at 8 a.m.
July 9. What?
That's the original invitation. It was sent on April 11th.
Alberto, maybe we should talk, give a warning to the people about the schedule.
Uh-huh. Yeah, I think that I can start, Eduardo. We start, okay?
Yes, we can start.
They're already recording this.
Yes.
Okay. We were waiting for Yifang to be logged, but we wait again. And let's go ahead for our LISHEP 2021 completely virtual. It's the first time that we do LISHEP without presential participation. It's unbelievable, but I can tell you that for me, it was much more work than in presential. It's very easy to understand because presential type, I had a secretary with me, and much more things we share, and the work is easiest. But presential, virtual, I have to do everything. Eduardo and I, we work without a stop all days up yesterday to do a lot of things because people had problems and write to us, even a lot of people that did not registration, we had to do the registration. And I am convinced that a small number of people read the bulletin, welcome bulletin with our information. But okay, then please do yourself the upload of your talk. If you don't, if you have difficulties to do that, please write to Eduardo or to us, to the LISHEP official promptly, and we do for you. We did even this morning early some of talks that people asked us to do. Our moderator today is in Portuguese because sometimes arrive. Dr. Gilvan Alves from Brazilian Center of Research. Gilvan is an habitué of LISHEP too. And this morning we will have the set of speakers, and the afternoon also another set of speakers. The number of speakers not means that everybody is the same time, no. Because as you know, LISHEP has two types of talk. All talks are invited talks, but some talk that is given for the to the collaborations, and then collaboration choose the speakers and send to us, is called the presentations. This presentation is 15 minutes. When we have a presential LISHEP, we have more time, but it's very difficult to do the same time in this type, this mode of to do a conference. And I am very happy with the program of this year, with very interesting subjects of high energy physics and complements, but mainly due to the so great people helping us to have very good days. And thank you, Dr. Yifang, if you are logged for accept our invitation. Then have a very good section C, LISHEP 2021. And thank you for your presence here in our LISHEP. Please, Jovan, you take now the moderation, the call, Harvey to do a few words also to Yifang. Thank you.
Thank you, Alberto. While we're waiting for Yifang, Harvey will say a few words to all the participants. Thank you, Harvey, for being here with us. So the floor is yours. Thanks. You're muted.
Thank you very much. Good morning, everyone. I'm very happy to be here at LISHEP 2021, even virtually. As you can see, I'm looking forward very much to coming back to Rio someday soon. And LISHEP is a great tradition, thanks to Professor Alberto Santoro over many years. And I think many of you know, there's not only Session C, which is a real high-energy physics conference with interesting subjects this year, with an emphasis on machine learning and also, among many interesting subjects, review of glue balls, but also an opportunity to bring high-energy physics and also some training to the Brazilian and Latin American community. And Session A is really focusing on teachers, which is also a wonderful aspect of the conference. Today and all days, 3 days of the conference, we're looking forward to very interesting presentations. And I'd like to thank all the speakers again for agreeing to join us virtually today through Thursday. So, welcome everyone.
Wang is connected.
Great. So Alberto,
Please, your microphone is closed.
Yes, I'll do the honors. Okay, so let me. Good morning, everybody. Good morning. So we start in LISHEP now. I'm going to introduce the first speaker. So Professor Yifang is the director of the Institute of High Energy Physics of the Chinese Academy of Science. He's also a foreign member of the Russian Academy of Science and fellow of the Third World Academy of Science. Yifang obtained his PhD in High Energy Physics in the University of Florence in Italy in 1992. He worked in many experiments around the world and led the design and construction of the BS3 experiment in the Beijing Electron-Positron Collider for Tau-Chan physics. He also led the Daya Bay reactor neutrino experiment and was the first observation of neutrino oscillation for the θ13 angle. He also proposed the JUNO neutrino experiment and the circular electron-positron collider as a Higgs factor for the future high-energy physics. So without delay, Professor Yifang, thank you for being with us. So the floor is yours. Thank you.
Thank you. Thank you very much for the invitation. Can you hear me?
Yes, we hear you.
Yes, yes, we hear you.
Okay, so great. So let me share my screen. Can you see my screen?
Yes.
Yes.
Okay, so I'm going to report the high-energy physics in China. First of all, we have our Beijing Electron-Positron Collider running at a 2.2 to 5 GeV energy range for Tau-Chan physics. And this machine has been operational since 2009. And indeed, last year, even during the pandemic, we managed to record highest peak and integral luminosity. And we managed to publish something like 37 papers last year, and in more than 300 in total. So a few highlights from this experiment. We observed a new resonance state, the ZCS. So this is actually a 4-quark state with CC bar in the US at an energy of, at mass of 3985. So this is strange quark with 2 charm quarks. We also observed damped oscillation behavior in the neutron form factors. This is very similar to what had been discovered at Babar for the PP bar oscillatory kind of behavior. And in left bottom, you can see that we managed to measure the hyperon up-down parameter with 7 sigma upward shift from previous measurement. So we also measured the gamma angle. We had a future plan. Since we had a very rich physics program requiring more than 40 inverse femtobark data, which corresponding to something like 15 years of data taking at the present luminosity. So we managed to come up with an upgrade plan to increase the luminosity by almost factor of 3. This has been can be achieved by squeeze the beam size, adding a new RF cavity per beam. And also we are going to replace the 2 superconducting quadrupole magnets near the interaction point to increase the maximum beam energy from 2.45 to 2.8 GeV. And both technologies, the RF cavity and also superconducting magnet, are actually a result of R&D effort for the circular electron positron collider at Higgs energy, Higgs mass energy. And this is actually a result of the CEPC technologies. We plan to finish this upgrade by the year of 2025, and the operation of the beam will continue until 2030. And the shutdown is planned for something like 6 months. So this is the best collaboration. We have something like 500 members from 74 institutions in 15 countries. The Daya Bay experiment has been managed to measure the mixing angle theta 13 to a very high precision. You can see from bottom left, the Daya Bay actually represents the best measurement for this mixing parameter. And indeed, the result from Daya Bay in the last year had this list of results. So we had optimum liquid scintillator recipe for JUNO using a Daya Bay module. And we also had the neutrino spectrum from uranium-235 and plutonium-239. And we also have the joint searches for stereoneutrinos by Daya Bay and aminos, and also a joint analysis of by Daya Bay and the prospect to measure the neutrino energy spectrum. Daya Bay actually determined to decommissioning, and data taking were terminated on December 12 last year. Indeed, the ceremony of this termination broadcast online, we had managed to attract something like 1.7 million viewers online. And the data analysis will continue, and we expect to have a precision of science where 2 theta 13 being less than 3%. You see right bottom the picture of the decommissioning, and we believe that we are going to finish the decommissioning in 2 or 3 months from now. The Daya Bay experiment consists of 41 institutions and 190 collaborators from 6 countries and the regions. Our next step for the neutrino experiment is JUNO, and this is a continuation of a react neutrino experiment used in the liquid scintillator. And the purpose of the experiment is for the neutrino mass hierarchy. The preparation started in the year of 2008. And you can see from this picture, our detector is going to see a 2-reactor complex, one called Taishan, another one called Yangjiang, a total of 8 reactors. And by using all the neutrino from 8 reactors, we are able to measure the neutrino mass hierarchy at the significance of 4 sigma in 6 years. And this measurement is going to be independent of CP phase. We can also measure neutrino mixing parameters with a precision of less than 1%. And having this kind of precision can allow us to have a test of the unitarity of the neutrino mixing matrix. We can also measure the, we can also have something like 5,000 neutrino events at a distance of 10 kpc from a burst supernova. And the discovery potential for the diffuse supernova neutrinos is at a level of more than 3 sigma for energy, for average neutrino energy more than 15 MeV. We can also study geoneutrinos, solar neutrinos, and also proton decays. So you can see from right bottom table, our precision improvement over the past measurement can reach something like almost factor of 10. The JUNO detector is a huge challenge. The size is almost a factor of 20 larger than the CamLand, with light yield a factor of 5 more. So we have built a huge cavern and a huge acrylic tank. And we need to have something like 20 kiloton liquid scintillator with the world best attenuation lens. And also we need something like a 20,000 20-inch foot tube with the highest detection efficiency, which is almost factor 2 higher than what the super decay obtained. This is a picture of the civil construction. You see the current status of a surface building near the entrance of the tunnel. And we have slope tunnel of 1.3 kilometers and also vertex shaft shown here on the right top. And this vertical shaft is about 600 meters. The blasting has been finished. We're now working on the water pool. You can see some of the pictures. And this is the water pool and also the top picture of the water pool. So detector construction is now in good shape. You can see from the picture, the top one is a critical panel, 9 meters long, 3 meters wide. And then this is steel structure and also a platform, you can see from the right bottom. This platform is going to support the construction of the acrylic panels. So this is a piece of acrylic panels. The sphere of the acrylic is going to be built on this platform. The detector installation will start very soon, and this shows you the practice of our workers to learn how to install photo tubes. All the photo tubes are actually produced and delivered, tested, and instrumented okay. So photo tube is actually our key ingredient for the experiment, and this was developed by IHEP with a Chinese company based on microchannel plate to collect photoelectrons instead of diodes. So intrinsically, this kind of design has higher collection efficiency and also easy for mass production. We successfully developed this new type of phototube with a detection efficiency more than 30%. And Hamamatsu managed to reach something like 27%. So we are almost 10% better than Hamamatsu. You can see this is without Hamamatsu, and this is LNVT. And also from this middle picture, you can see that the uniformity of this macro channel plate is also better than what Hamamatsu obtained. We are also going to build a new detector for the JUNO experiment. We call the JUNO Tau. This is a liquid scintillator detector running at -50 degrees. By having this kind of detector, we can have a precise measurement of the reactor neutrino spectrum with sub-percent energy resolution. We plan to use 10 square meters of silicon PM with more than 90% of coverage, and the detection efficiency is more than 50%. So by having this kind of design, we can reach something like 4,500 photoelectrons per MeV, and this is factor 3 better than JUNO. But in order to have this kind of performance, we need to cool down the liquid scintillator or the silicon PM to reduce its dark noise by 3 orders of magnitude. So silicon PM has to run at -50 degrees, so the liquid scintillator also has to work at -50 degrees. So this is actually a complete new design, and we plan to have something like 2,000 neutrino events per day, and the background is less than 10%. So this is actually a very normal design, and the construction is underway. In the future, we believe that the neutrino physics will turn to the double beta decays and also for the neutrino absolute mass determination. The reason is following. We know from cosmology, neutrino mass has to be less than 1 eV, and our guess from the oscillation is that the neutrino mass is something like 1 milli eV. However, beta decays can probe only up to the level of 200 milli eV, and neutrino-less double beta decays indeed can target at something like 1 milli eV. So this is a list of new experiments planned for the double beta decay searches. Most of them has a mass of something like 1 to 10 tons. But the JUNO experiment can actually host something like 50 to 100 tons of the target. And indeed, it can be very close to the 1 milli eV. The reason we shoot for 1 milli eV is the following. You see from this picture, the right top, if you are able to reach neutrino double beta decay, the effective mass of 1 milli eV, the sum of all neutrino energies will be determined to a very narrow range from 0.06 to 0.07 eV, 6 to 70 milli eV. So if this sum is determined, then the beta decay effective mass is going to be determined. And once these two are determined, then also M1, the lightest neutrino mass, is determined. And if M1 is determined, of course, we know delta M1, M2, and the delta M2, M3. So M2, M3 will be determined. So then in this case, the neutrino mass will be all determined, and the issue is completely resolved. And also from left bottom picture, you can see that the Majorana phase rho is determined if you are able to reach 1 milli eV. Of course, with large error, but more or less you can determine this. And by having the sensitivity of the double beta decay mass determination of 1 milli eV to 0.1 milli eV, indeed, there are almost no space for parameters to less than 0.1 eV. So we should be able to see that neutrino-less double beta decay being seen or ruled out. So actually shooting for 1 milli eV or even further in the far future, 0.1 milli eV is actually a final goal of our neutrino physicists. This is a JUNO collaboration. We have more than 600 members from 77 institutions and 17 countries. In the further future, we plan to work on a Higgs factory we call the CEPC. Indeed, since the year of 2005, we were discussing the next machine after BPC. And the idea in the end came up to a circular E+- collider followed by a super proton-proton collider, which was all proposed in the year of 2012. And indeed, it quickly gained momentum in China, in LISHEP, and also in the world. By looking at the new physics at E+- collider, we can actually go for direct searches of new physics afterwards in a proton-proton collider. Indeed, the 100 kilometers tunnel can be reused for proton-proton or ion-ion or electron-proton colliders up to even 100 TeV. So this compatibility study should actually start it now. This is our design of the CEPC layout. We have a collider ring, and this is double ring machine. And then we also have a booster. And booster is going to accelerate the beam energies from 10 GeV up to the Higgs mass, and even higher to the TT bar energy range, 170 GeV. And this injector is actually a LINAC with a length of 1.2 kilometers up to the energy of 10 GeV. So our baseline design is 100 kilometers of circumference. A total power is 30 megawatt, upgradable to 50 megawatt, and upgradable to high Lumi Z option, and even upgradable to TT bar energy. And the machine has to be compatible to the PP collider. This is a list of all the parameters of this machine running at Higgs and also Z. We didn't list the TT bar. I think we also have a complete parameters for that. The luminosity for the Higgs is 5 times 10 to the 34, and the luminosity for the Higgs for the Z is 1 times 10 to 36. So this is actually almost a factor of 10,000 over what has been reached by the lab experiment. So we have been working on accelerator R&D in the past 5 to 7 years. For example, we worked on the polarized electron gun, high current positron source, superconducting RF cavity, and high efficiency klystrons, low field dipole magnets, vacuum system, separator, and also high TC superconducting magnets. So, for example, for the RF cavity, we have been working on different R&D projects like nitrogen doping, mid-temperature baking, and so on. We also invented a new method to process the cavity. It's called the flexible polishing to replace bulk electron polishing. So this method can actually have very high efficiency and also environmental friendly and low cost. You can see the effect of this so-called flexible polishing. R&D are still going on. We had a few prototypes using different technologies. For example, this 1.3 gigahertz 9-cell high-Q cavity already satisfied the requirement of CEPC and also Shanghai free electron laser source project. Based on this method is based on the mid-temperature furnace baking. We also have the high gradient cavity close to the requirement of IRC. You see the picture here. This is IRC spec, and this is our result. So we are actually, this is our result. You can see we are very close to the IRC spec, and these dots are the result of our measurement, and these are the spec. You see, we already exceeding the spec of LCS2 and also CPC. We are also working on 650 megahertz 2-cell high-Q cavity. And also we are trying to see if we're able to have a very high Q and a very high gradient cavity. By having this, we can use only one cell cavity. You see from this picture, we are still steps away, and we're still working on it. We hope that we can join in the future the ISC effort for the IF cavities and also clystrons. This is our R&D for the iron-based high TC magnets. We managed to build the world's first iron-based connecting coil running at up to 24 Tesla. And this is a demonstration that indeed iron-based connecting coils can produce very high magnets. And this one shows you that IBS are very promising for the high field magnet. This is for a coil, bigger coil. We're also working on the detector design. You probably heard that we had many detector design for the International Linear Collider. This top left is ILD type of detector, and left bottom is SID type of detector, and right top is a new design by IDEA Group for the FCC and the CEPC. So this is a very famous IDEA concept. We very recently proposed a so-called false concept. We still need to invent a name for it. And this is actually based on silicon pixel, a vertex detector, a silicon tracker plus a drift chamber for tracking and for the particle ID. And we may have a timing detector, and we have a crystal calorimeter for the particle flow algorithm, and a thin magnet running at 2 to 3 Tesla, and also hadron calorimeter. This 3D crystal calorimeter with PFA capabilities can provide you a detector, EM calorimeter with energy resolution of 3% over square root of E, which is at least a factor of 5 better than the so-called silicon tungsten kind of sampling electromagnetic calorimeter. So this design have a list of advantages. It's very good energy resolution, 3D shower information with limited readout channel, and also a very effective molecular radius, which is very similar to the silicon tungsten. You can see from this picture, the arrangement of crystals is actually XY kind of arrangement of the crystal bars, and beam shooting perpendicular to the crystal bars. This is a very novel design, but we had to remove the very famous ambiguity. And this ambiguity is removed by the measurement of timing at 2 ends of the detector. And the precision of the timing measurement can be very close to something like 3 to 5 centimeters. So we are now working on the software to have a 3D shower reconstruction and try to get a jet reconstruction and the PFA algorithms working. This kind of detector concept could, in principle, work also in for the ISC and also for FCC project. This picture shows you we managed to reconstruct 2 photons with a distance of roughly 5 centimeters. They are very well separated. So in summary, sorry, I went a bit too fast. BPC Batch 3 will continue until 2030 with minor upgrades. And the Daya Bay has been terminated. JUNO construction is in progress. Data taking is planned in 2023. CEPC design R&D is in good shape. Construction still in the process of the request. However, I didn't mention very much. We also have a long list of astrophysics program in good shape. Just give you one example. We have a cosmic ray experiment at very high altitude called the LASO with altitude of 4,000 meters. This is actually a combination of large air shower arrays with capabilities for electrons, muons. It also have a Cherenkov telescope and the water Cherenkov detectors. They are actually very good for cosmic ray studies and also gamma ray astronomy. The construction has been finished and data taking has been started. With partial data taking, we already obtained very important results recently just published on Nature and also another one to be published on Science. We observed the highest gamma rays from the Milky Way with the energy of 1.4 PeV. Before that, and I think 2 years ago, people were only managed to observe something like 0.4, 0.5 PeV. We identified 12 sources of gamma rays in the Milky Way with energy up to 1 PeV. This shows that our Milky Way are full of perotrons, the accelerators which are able to accelerate the protons to energy way more than 1 PeV. So this is actually a very important discovery which can tell us where the high energy cosmic rays comes from. And this is actually a way, steps towards a full understanding of the origin and the acceleration mechanism of cosmic rays. So this is actually a very important result. So I will stop here and ready to take questions. Thank you.
Thank you, Professor Wang, for this great talk. I just forgot to remind people that in order to do the questions, to use the Q&A button at the bottom of the panel. Good. So I got a question here from Roberto, from Rogerio, about the CEPC. Is asking if the CEPC is an international collaboration yet, or?
Yes, CEPC, the design is already an international collaboration. If you look at the conceptual design report, among all the 1,000 authors, more than 1/3 are international authors. We are certain that in the future, more international participants will happen.
Mm-hmm. Yeah, since I am running this, I'm going to make my question. How about the CEPC versus the FCC is being also projected by CERN and the people. So how do you see this competition?
Well, I think at this stage, competition and the collaboration are both needed. First of all, from technical point of view, we are actually exchange a lot of information, so we are collaborating. But on the other hand, the project we need to approach to our funding agencies, and having some kind of competition is actually good. So we can both tell our funding agencies that, look, if you are not fast enough, somebody else will do it. So I think it's good for all of us, for our community.
Yeah, great. Rogerio also has a question about not only the accelerator itself, but the detectors. Do you have already a collaboration going on for the future detectors on CEPC?
Yes, we do have international advisory committee, and in each of the technical groups, we do have international members for vertex detector, for tracking, and for calorimeter and so on. For each sub detectors, we do have international members in our weekly meetings. We have something like 1/3 of international participants. However, we haven't really come to an international collaboration for any of the detector concept. So we are still working on individual technologies, and we are going to release call for letter of intent or call for proposals in the future. Only by that time, a very formal international collaboration can be formed.
Mm-hmm. Great, thank you very much.
You're welcome.
I don't see any other questions, so I thank you again, Professor Wang, and
Thank you.
thank you very much for your excellent talk. And I hope we can collaborate with you sometime in the future. That'd be great.
We
Sure,
hope to
absolutely.
have more collaboration with Brazil too.
Yeah,
Absolutely.
that'll be.
By the way, we do have a Brazilian collaborators to the JUNO experiment. So we are happy to collaborate further in other projects, of course, including the CEPC.
Mm-hmm. No, that'll be great. Thank you.
One, if
Yes.
Professor Jesse Thaler agrees, we can go ahead.
Yeah. So, Professor Thaler, are you ready for your talk? Because we are way ahead of schedule, but anyway, if you're ready, we can switch the talks right now.
Sure, that's fine by me. Absolutely.
Okay. Great. Thank you. Thank you very much for agreeing to go for a bit earlier. So let me introduce you. Yes, before I forgot to tell in the beginning. Please send your questions in the Q&A button at the bottom. So you have the Q&A button in the bottom. So the chat in principle is just for us to talk about. The questions should be asked in the Q&A button at the bottom in the screen. So in principle, we way ahead of schedule, so there's no problem with timing. So let me just introduce Professor Thaler. So Professor Thaler is a theoretical particle physicist, which uses techniques from quantum field theory and machine learning, addressing outstanding questions in fundamental physics. His current research is focusing maximizing the discovery potential at the LHC to the theoretical frameworks and novel data analysis techniques. Professor Thaler joined the MIT Physics Department in 2010 and currently an associate professor at the Center of Theoretical Physics. In last year, actually 2020, he became the inaugural director at the NSF Institute for Artificial Intelligence and Fundamental Interactions. So without further ado, Professor Thaler, the floor is yours. Thank you.
Great. Well, thanks very much for the invitation to come to you all virtually to Brazil. And I'll be talking about artificial intelligence and fundamental physics. And so as Gilvin said, I'm now the director of a new Institute for Artificial Intelligence and Fundamental Interactions. This is a collaboration that's taking place in the Boston area between MIT, Harvard, Northeastern, and Tufts, where our goal is to advance physics knowledge from the smallest building blocks of nature to the largest structures in the universe, as well as galvanizing AI research innovation. And one way of trying to explain what we're trying to do in this institute, and you're going to see threads of this through this talk today, is to develop what we're trying to call ab initio artificial intelligence. So ab initio from first principles. And we're trying to take machine learning techniques and incorporate first principles, best practices, and domain knowledge from fundamental physics. And so some of the things that I'll be talking about today are things like symmetries, conservation laws, as well as trying to have things that are verifiable, guarantees of exactness. And these are things that as physicists, we certainly do in our research without artificial intelligence. And the question is, when we start to incorporate AI into our research, can we also maintain these same high standards of scientific reasoning? So when I first encountered this field, I was quite skeptical that it was possible to do machine learning that incorporated domain knowledge from fundamental physics. I viewed machine learning as being kind of a black box, and how would you ever possibly be able to understand what's going on inside that black box? And around 4 years ago, I changed my mind, and let me show you one of the examples that helped change my mind to start off the talk. An example that doesn't come from physics, but comes from the field of computer vision. And so this is a computer vision task, which is quite standard. It's called an in-painting task, where on the left-hand side, you see a picture of a library with various regions of this library masked out. And on the right-hand side, you see a reconstructed image where you're trying to fill in the gaps that are coming from the masked region. And the standard story in deep learning for how this task is even possible to solve is, one, we have increased computational power, which means that we can search through a huge space of possibilities to try to find the best reconstruction of this image, but also that we have very large data sets, such that you have many examples of libraries, and you can basically use that to build up a prior distribution for what you think libraries in general look like. And then you can figure out, given this library on the left-hand side, what's the best reconstruction on the right-hand side. So that's a standard story in deep learning, and it's been very powerful over the years. But what really influenced me about this particular example, again, this comes from the computer vision literature, is that in this case, the neural network that was used to solve this problem had never before seen any images of libraries whatsoever. And so I would call this deep learning meets deep thinking, that here we actually just have a randomly initialized neural network, one that doesn't actually have any knowledge whatsoever about what libraries look like. And instead, progress is made in this case by understanding the structure of the problem to be solved. So it's not just increased computational power, it's not just large data sets, it's understanding the structure of the problem that we're trying to address. And in this particular case, what we're taking advantage of is we're taking advantage of the technology of convolutional neural networks. And in the language of physics, convolutional neural networks incorporate a symmetry, namely translational symmetry. And in trying to fill in these gaps, these masked regions, you're taking advantage of that translational symmetry to basically be able to mask, being able to copy pieces of the library and basically translate them across the image. And so in physics, we understand a lot about the structure of the problems that we're trying to solve. And so it's not surprising that, yes, there's increased computational power. Yes, there's large data sets that we can use, but also there's first principles that we can leverage for our machine learning technologies. And that's what I'll be talking more about in this talk today. So just to give you an example from my colleagues at the Institute for Artificial Intelligence and Fundamental Interactions. So here's a wonderful collaboration led by Fiala Shanahan about using this ab initio AI for theoretical physics. And I have in the backup slides examples from experimental physics as well as from foundational AI for people who are interested. But this is the case of lattice field theory for nuclear particle physics. So as we know, the equations governing the strong nuclear force are well known, but precision computations are extremely demanding. So if you look at supercomputing resources in the United States, about 10% of that, of open supercomputing resources, are used for lattice field theory calculations. And these lattice field theory calculations are relevant for all sorts of things: dark matter detection, neutrinoless double beta decay, proton-proton fusion, understanding the QCD phase structure, things like that. And there's been an exciting collaboration with academia and industry to develop custom AI tools. And here you have this coming together of the AI community and the physics community. From the AI side, a 1,000-fold acceleration in lattice field theory calculations has been achieved using a custom generative model based on normalizing flows. So that's a technology coming from the AI community. Coming from the physics side, there's a strategy to preserve the symmetries of the problem, the symmetries on the lattice, including gauge symmetries, as well as guarantees of exactness, such that if you took enough samples, you'd actually be able to get the exact answer asymptotically. And so this is this fusion between deep learning and deep thinking. And then the payoff here is actually that the tools that you develop in this context have actually found interdisciplinary applications, because in the context of lattice field theory, there are compact symmetries that you want to preserve. And for example, in robotics, you also have compact U1 symmetries that govern, for example, the motion of robot arms. And so these tools that are coming from the physics literature are also relevant beyond. So this is just one example of kind of this fusion of artificial intelligence and fundamental physics, and I'll be giving you more examples from my research in this talk. So maybe to set the stage a little bit for those of you who don't use machine learning already in your research, let me talk a little bit about the lens of machine learning and what formalisms are needed to leverage machine learning for high energy physics, or really for any scientific application, and what techniques do you have to learn, or what mathematics do you have to learn in order to take advantage of these technologies. So I'm going to start with a relatively simple problem. This is something that's known as the likelihood ratio trick. And it's an example of something that's being called in literature simulation-based inference. That is, in particle physics, we have fantastic simulations of how particles are produced and the way that those particles interact with detectors. And based on the simulations, we can try to do a variety of inference tasks. And it turns out that many high energy physics problems can be expressed in this form. I'll give you a couple examples in this talk, but I have more in the backup slides. So let's say my goal is to estimate this likelihood ratio, the likelihood of P of X, so X is some feature of my collider data, let's say, divided by Q of X. And this likelihood ratio can be used for all sorts of applications. For example, in the discovery of new physics, you'd want to do a kind of maximum likelihood search over possibilities. And let's say what I'm given is I'm given finite trading samples from some simulation of capital P and capital Q. And I'm given a function f of x that's flexible. It has a bunch of parameters that I can adjust those parameters. And the parameters, let's say, by parameterized, for example, by a neural network. The details of this parameterization aren't relevant for, or aren't particularly important for this example here. So then I write down a loss function. So L is the expectation value over the sample P of log of f of x. And the second term is the difference of f and 1, expectation over the sample Q. And one can show with a little bit of work that asymptotically, the minimum of this loss is indeed achieved when f is equal to the likelihood ratio P over Q. And the actual value of the loss is related to a statistical divergence called the KL divergence. So this slide here is very standard. This is what is standard machine learning 101. But I think to physicists, this might look a little bit strange and daunting and very stats heavy. And one of the things that helped to understand kind of what's going on here is translating this statistics language into something that's more familiar to a physicist. And it turns out that all we're talking about here, asymptotically at least, if I have large training data sets, it's this exact same structure as we have for Lagrangian mechanics. So we have an action, L. Normally it's an integral over time, but here just replacing time by the symbol X. We have a Lagrangian. This Lagrangian involves the probability density P, the probability density Q, and then this function that I'm trying to learn, f of x. And then the equivalent of the Euler-Lagrange equation, basically trying to find the extrema of this action, that Euler-Lagrange equation, the solution to that with a little bit of algebra, you can convince yourself is precisely that likelihood ratio P over Q. So actually, even though the language on the previous slide was written in a more statistics language, it's actually quite familiar to a physicist what we're trying to do. And it also explains why we have freedom when we're doing machine learning to specify the problem that we want. So instead of trying to solve a problem, we can just specify it in terms of some function to be optimized. And then we can use the machine to try to do numerically find the solution to the Euler-Lagrange equation given finite training samples. But this also, again, emphasizes that we as physicists get to decide the structure of the problem that we're trying to solve, as well as any symmetries or features that we want to embed into the function f that we're trying to learn. So in general, what are the requirements if you want to leverage machine learning for your research? If you have in hand some well-specified loss, and again, you as the researcher get to choose that, some reliable training data taken, for example, in the particle physics context from let's say, simulation, and some learnable function that you can adjust the parameters of to try to find the best optimum for the problem that you want to solve, then you can leverage machine learning. And many, many high energy physics tasks can be phrased in this language. And the thing I want to emphasize is that physics input is essential for the robust usage of these tools. Okay, so now I want to transition a bit to talking more specifically about high energy physics. So we're going to hear more about machine learning and high energy physics in the talks coming up by Heather, Javier, and Anima. My own research specialty are jets. Jets are collimated sprays that come from the fragmentation of quarks and gluons. And I've used a variety of both machine learning and non-machine learning strategies to analyze the substructure of jets and trying to figure out what the underlying short distance physics is. People are interested, and I could talk more about other applications of machine learning for high energy physics, though I think Javier is going to be talking a lot about that in his talk later on. And what I want to do is I want to try to explain to you in the context of high energy physics, how did I transition? How did I transition from a curmudgeon to an evangelist? So 4 years ago, I used to make jokes about my friends who were using deep learning for their research, and basically the slide that I had earlier about deep learning and deep thinking. As a theoretical physicist, I thought that deep thinking was a superior way to tackle physics tasks compared to deep learning, and I've changed my mind. And what I'm going to try to do is tell you about some helpful guides for me in pursuing machine learning for high energy physics in my research, and hopefully that will inspire you to also incorporate more machine learning in the work that you've been doing. And so the questions that I had when entering this field, here's a couple of them that I'll try to walk you through. The first one is, can theoretical structures be encoded directly into the machine learning architecture? I mean, part of what made me skeptical about machine learning was that machine learning seemed like a black box, and it seemed different from the kinds of techniques that we typically would do in physics, in particular in theoretical physics. So is it possible to encode theoretical structures directly into your machine learning architecture? The second question was, can your strategy to be defined on physical quantities? I just talked about simulation-based inference and the fact that we can do a variety of machine learning tasks based on simulation, but simulated data is not the same as real-world data. And is it possible to do machine learning where you can define things directly on the things that you can measure? And then finally, a lot of the progress has been made in machine learning using supervised machine learning. Supervised machine learning are machine learning strategies where you, in some sense, already know what the answer is, where your data is labeled in some way, and you're trying to figure out, based on the information that you have, how to extract those labels. But what if you have unlabeled data? Is it possible for the machine, in some sense, to find structures for itself without relying on someone already telling you, in some sense, what the answer is? So I'll walk you through these examples, again, all coming from my, my research program. Okay, so let's start off with the question, can theoretical structures be encoded directly? And let me tell you a little bit about jet formation and a particular way of representing information called the energy flow representation. So at colliders, like the Large Hadron Collider, we slam together protons at short distances. Protons are bags of quarks and gluons, and a common thing that happens when you slam together protons is that you make high energy quarks and gluons. These quarks and gluons shower and fragment, and eventually, because of the confining interactions of the strong force, they form composite hadrons, and those composite hadrons eventually hit your detector. And it's a challenging inference task to figure out, based on the particles that are reconstructed in your detector, can you figure out what was actually happening in the original hard collision? So that's the problem that you'd like to solve. Now, this is a challenging problem on the theoretical side, in particular, because the dynamics of hadronization is not perfectly known. And also we have the complications of detector effects. But one of the things that we know from the theory side is that there is information, what we call infrared and collinear safe information, that is relatively robust to the smearing effects of hadronization and detection. So from the theory side, if I want to do a perturbative field theory calculation, I'd like to focus on the flow of energy from the collision point off to infinity. And that's the thing that I can actually compute order by order in a perturbative expansion. So this energy flow operator, it's a quantum mechanical operator. It's built out of the stress energy tensor T mu nu. So T0, that's the energy, and I is the flow, so the flow of energy from the collision point off to infinity. And this energy flow operator is robust to hadronization effects. It's robust to detector effects. That is, we have controlled corrections to the perturbative calculations due to hadronization, and we can actually watch those corrections decrease in importance as you go to higher and higher energies. This is something that's well-defined for massless gauge theories like QCD, so it's perfectly well-defined, unlike, for example, the scattering matrix, which has some ambiguities due to massless degrees of freedom. And what we'd like to do is we'd like to build a machine learning architecture that's built around this energy flow representation. So this is an idea of incorporating our theoretical structures into our machine learning approach. So with my collaborators, Patrick Kamitsky and Eric Metodiev, we were able to do this. We built a neural network architecture called energy flow networks. And it's an architecture designed around this particular symmetry, the symmetry having to do with infrared and collinear safety. And this is just one of a variety of strategies that people have been developing in particle physics to embed the symmetries that we know into our neural network architectures. So for example, there's been some exciting work that's linked here about building in Lorentz symmetries into neural network architectures. But this energy flow network is relatively simple. We have a problem that we're trying to solve. The solution to some problem that we're trying to solve involving jets can be written in this interesting factorized form. We have a function f that takes as inputs these various v's, v1, v2, all the way up to vl. And each of the vas is a function of the jet, but it's a very special function of the jet. It's a function of the jet where I sum over all the constituents of the jet. and I weight it by the energy of the particle multiplied by some function phi that takes the direction of the particle into account. And this structure here is special. It's special because it has symmetries built into it. So one of the things that we know from quantum mechanics is that identical particles are indistinguishable. Therefore, the order in which I see the particles has no physical meaning. And so the permutation invariance on final state particles is enforced in this neural network architecture by doing a sum. And this sum makes sure that the order of particles doesn't matter for the task that I'm trying to solve. Then this energy weighting that's linear, this enforces this principle of infrared and collinear safety. And then everything else is a learned function, learned by neural networks, where arbitrary functions of the directions can be used, and then arbitrary combinations of these V's and this final F can be used to figure out the solution. So I've baked in my symmetries, which is good, but then I've given it also the flexibility that neural networks have to find the optimal solution to whatever problem that I'm trying to solve. So it turns out, based on work that a computer science group at Carnegie Mellon did, that this structure turns out to provably describe any safe observable. So anything that's infrared and collinear safe can be written in this form. It turns out to have excellent performance for a variety of tasks, including jet classification, for example, telling the difference between whether I have a quark jet or a gluon jet being produced. But the thing that I really like about these energy flow networks is that they offer us a chance to interpret what the neural network has learned. And this interpretability is something that I think is very powerful and something that gave me confidence that the machine was doing something sensible. So this V function, this V really stands for verification, that these V functions are ones that I can just plot and make pictures of. In particular, it's this phi function that's easy to plot. It's just a function of the directions that particles are going. So if I have my collision here and I watch the flow of energy going off to infinity, each of these phi functions, you can interpret that as the neural network paying attention to different regions in this energy flow space, basically different regions in the flow of energy off to infinity and where it's paying attention to. Now, if this L is sufficiently big, it's hard to plot all these functions at the same time, but I'm going to do my best. So we're going to learn 256 of these internal or so-called latent dimensions. And then we're going to try to plot all 256 at the same time and see what the network has learned. And what you get is you get this psychedelic network visualization that turns out to have a huge amount of science baked into it. So we've taken all of our jets, we've pointed them in a particular direction, we've pointed them such that they're all flowing into the center of this image here. And the thing that your brain immediately notices is that there's a symmetry azimuthally going around the jet axis. So that is, the neural network is paying attention to information in a way that's azimuthally symmetric around the jet axis. And this makes sense. We're dealing with unpolarized jets, therefore it should be paying attention to information in a uniform way. But maybe the more exciting thing is that you see from these rings are bigger near the outside and smaller towards the center. And you can think about each of these rings as enclosing a region that the neural network is trying to pay attention to. And you see that the neural network is paying more and more and more and more attention to the center of the jet. And when I first saw this, it was absolutely fascinating to me that the neural network had basically learned something that we teach our students in quantum field theory. We teach them about the collinear singularity structure of the strong force. And indeed, the machine had learned that for itself. So again, the task that I'm trying to solve here is telling the difference between quark jets and gluon jets. And I'll say a little bit more about that in a few slides. But we know from quantum field theory that the way that quark and gluon jets form is that you have a hard central core that carries color charge 4/3 for quarks and 3 for gluons. And that color charge tells you how much gluonic radiation comes off of that hard central core. And the amount of gluonic radiation is proportional to the strong coupling constant alpha S. It's proportional to the color factor. And in terms of kinematics, it has this collinear singularity that tells you that there's more prevalence of radiation towards the center versus the periphery. And then the soft singularity that tells you that the radiation tends to be at lower energy. And what you're seeing in the psychedelic image is you're seeing precisely this collinear singularity mapped now to the pixel size that I'm learning compared to the radial distance away from the central jet axis. And you get this power law behavior here, where if I just had this Altarelli-Parisi splitting form, then I would have gotten a slope of just 2. The fact that the best fit slope is 1.6 is due to running coupling and non-perturbative effects. But nevertheless, the scaling behavior is something that the machine was able to learn. And this is quite exciting for me. We gave the machine two symmetries. We gave it permutation and invariance and infrared and collinear safety. And it was able to learn for itself that the best way of solving this jet classification task was to also encode this kind of scaling symmetry that we know about from the strong force. So can theoretical structures be encoded directly? And energy flow networks are an example of that, where we can combine infrared and collinear safety with permutation invariance to get a very powerful and flexible neural network framework for jet physics. Okay, so let me now turn to my second example, which is, can strategies for neural networks be defined on physical quantities? And the example that I just showed you was a example of quark-gluon classification, which you can think about as being kind of the hello world of jet physics. It's a very simple binary classification. Is it a quark? Is it a gluon? And the goal of these classification tasks is to learn some function h, such that if the jet that was given was a quark, you output 1. If the jet that you're given was a gluon, you would output 0. And it turns out that you can't get perfect separation between quark jets and gluon jets. The best that you can do is saturate the so-called Neyman-Pearson lemma. And the best H that you can find is one that is based on this likelihood ratio. So this likelihood ratio trick that I told you at the first part of my talk, you can, with a little bit of manipulation, turn it into the optimal binary classifier and vice versa. This is why this is such a versatile and ubiquitous tool that we see in high energy physics. And you can kind of see how this thing works. If I'm in a region of phase space where the probability of getting the jet from gluons is 0, then I get 1 as desired. And if the probability of getting gluon jets is much, much larger than for quarks, then this thing turns into so 1 before, and then it turns into 0 in the gluon case. Okay, so this is all very standard, but you should be concerned about this framework, because what do you mean by a quark jet and a gluon jet? Quarks and gluons can't be seen directly in nature. They of course confine. And what we see in our detector are jets, which are clusters of colorless hadrons like pions and kaons. We never see a quark or gluon in isolation. And while we have simulation tools that allow us to label jets as quark and gluon, parton shower truth, that is the outcome of these simulation tools and the internal structure of the simulation tools, is essentially a fiction. It's something that we're using to generate example jets, but we don't actually have jets that come out of the detector saying, hi, I'm a quark, hi, I'm a gluon. It's fundamentally ambiguous what we mean by a quark or a gluon jet. Okay, so I could do this jet classification task, but what really am I doing? And this is one of the things that made me very skeptical about applying machine learning, because it seemed like whatever biases or limitations to my simulation that I might have, that those biases and limitations would just be transferred directly into the machine learning approach. But what I was delighted to learn was that there is a field of machine learning having to do with natural language processing and trying to take documents and disentangle documents into component themes that can be leveraged in the context of jet physics. So in the natural language processing literature, this is known as topic modeling, and we can use that to disentangle jet categories. So it's certainly true that you can't unambiguously label individual jets. I can't tell you that this jet is a quark, this jet is a gluon, this jet is a boosted W boson, this jet is a boosted top quark. I can't do that. But nevertheless, you can extract quark and gluon distributions from hadron level measurements. So this is shown on the left-hand side here, where I have a sample of Z plus jets in purple, a sample of di jets in pink, and these are some kind of mixture of quark and gluon. And I can apply this natural language processing technique to disentangle this into topic 1 and topic 2, disentangle these histograms into their component distributions, which align actually quite nicely with the quark and gluon artificial labels that come out of a simulation tool like Pythia. And you might ask, well, how is this possible? How is it possible to take a stack of documents, or in this case, a stack of histograms, and disentangle them into their component pieces? And the trick from this natural language processing literature is to use the concept that's known as anchor words. So if I say the word energy, energy could come from a physics context or it could come from a client science context. If I say the words energy conservation, of course, has a physics meaning, but it also has a meaning in the context of climate science. But if I say the word Noether's theorem, of course, is a physics concept, where if I say something like Kyoto Protocol, that's, of course, coming from the climate science literature. And you can take those anchor words, that is words that are unique to one field or the other, and use that actually to bootstrap your way to an understanding of the full distribution. So in the case of quarks and gluons, you're trying to find those regions of phase space which are dominantly quark and the regions of phase space that are dominantly gluon. You can isolate those categories in this kind of extreme region of phase space and then use that to bootstrap out the full distribution. So a very powerful technique that allows us to define at hadron level what we mean by the parton level, quark and gluon, in an operational way facilitated by machine learning. So can our strategies be defined on physical quantities? The answer is yes. And this technique that we call jet topics is a hadron level approach to try to understand QCD partons, allowing us to do something that from a theoretical perspective is actually quite ambiguous, but from a machine learning perspective, we at least have a concrete algorithm that allows you to do this disentangling. Okay, the last example that I want to use for my research is one about leveraging unsupervised machine learning. And this is an example that was quite a surprise to me. I was really excited about this whole field that I had no idea existed that turns out to be relevant for high energy physics. So the starting point here is a technique that again comes from computer vision. That's something that's called the Earth mover's distance, which actually has a long history going back to a French mathematician, Monge, who was trying to figure out how to transport dirt or earth, transport dirt from one configuration to another. This is like trying to build a ditch and take that ditch and try to make an embankment. And more generally, optimal transport problems, which show up in computer vision, are trying to compute the minimum amount of work, that is the amount of stuff or dirt that I need to move times the amount of distance that I need to move it, to make one distribution look like another one. So in the context of computer image processing, you can imagine that you have a black and white image and the pixel intensity corresponds to the dirt. And then you want to ask how similar is one image compared to another one. And you can do that by solving an optimal transport problem. And more generally in the sciences, anytime you have some notion of an additive weight and some notion of a ground distance, you can compute the amount of work to make one distribution, here shown in blue, look like another one, here shown in red. And that gives you a distance between distributions. And this is something that's a very powerful thing to have, assuming that your data takes a distributional form. And the reason why this is popular in the machine learning literature is that this Earth mover's distance is basically doing a horizontal comparison of distributions. So I have a blue Gaussian here and a red Gaussian here, and I'm trying to ask how similar are the red and the blue Gaussians. And the energy movers, or the Earth mover's distance rather, is a horizontal comparison between blue and red that takes into account the stuff that I have times the distance that I have to move it over. Whereas other types of statistical tests like the KL divergence are vertical comparisons. And vertical comparisons are excellent, assuming that the distributions have a lot of overlap. But once I take these Gaussians and move them further and further apart, they stop having any vertical overlap whatsoever. And you don't actually get that much dynamic range when these histograms get further and further apart. Whereas with this horizontal comparison, as the distributions get further and further apart, the EMD gets bigger and bigger and bigger, and you get a lot better dynamic range compared to this vertical comparison. So because of this, we actually see the use of the EMD growing in the machine learning literature. And the name that this often goes under is the name of the Wasserstein metric. And so the word Wasserstein, if you haven't known what that word means before, it basically means this horizontal comparison of distributions. Now, in the particle physics context, how are we going to leverage this idea? And what we did in our research is we defined a generalization called the energy mover's distance, where what we're trying to move around are energies. I told you earlier about infrared and collinear safety and the idea of weighting particles by their energy. So you can think about an idealized calorimeter that measures the amount of energy that's flowing into some part of the calorimeter. So here I have a blue jet shown here with the amount of energy that's deposited into an idealized calorimeter, where again, the center of the jet is at the center of this image. I have another jet in red showing you the flow of energy into that calorimeter. And what the energy mover's distance is trying to do is it's trying to say, what's the best way of optimally rearranging the red energy to look like the blue? This energy mover's distance has units of GeV. It takes in two energy densities and it spits back a number. And this number involves two terms. One term is the standard Earth mover's distance, albeit now adapted to moving energy around. So this F is the amount of energy that I'm moving from one location to another. Theta is the distance that I'm moving that energy. We have one term that involves the cost to move energy, and the other term that involves the cost of creating energy in the case where I have two jets that have unequal energies. Okay, so this is something that we're just taking from the machine learning literature, and it's unsupervised. I don't have to tell you anything about these jets, where they come from, whether they're quarks and gluons. All I say is compute this quantity and see what numbers you get and figure out what you want to do with that information later. Now, what's really interesting about this energy mover's distance is that it defines a metric on the space of events. So metric here doesn't mean metric in the general relativity sense. It means metric in the computational geometry sense. So a pairwise distance between configurations. And this metric satisfies the triangle inequality, meaning that if I want to go from the red configuration, so imagine this energy flow in red being mapped to a single point in this new abstract emergent space. The blue energy flow is mapped to a single point in this emergent space. And if I want to transport from red to blue, it's cheaper to do that transport directly than if I had a third energy flow in green, going from red to green and green to blue. That's always bigger. So that's satisfying the triangle inequality. And once you satisfy the triangle inequality, you can now triangulate a space just from those pairwise distances and now ask interesting questions about that space, which are different than the standard questions that we ask in fundamental physics. So let me show you just one example. Maybe I'll have, one example of something that I can do in an unsupervised learning way. I can compute the dimensionality of the space of jets. And this is not something that we usually think about doing. Normally we think about taking events, putting them into histograms, studying those histograms. Here instead, I'm taking pairs of jets, computing their distance, and learning something about the whole space that's triangulated by those distances. And one of the things you might want to know is what's the dimensionality of that space. And there's a standard method that's used in for studying the dimensionality of fractals, where you take advantage of the fact that if you want to know the dimensionality of your space, you can figure that out by calculating for any given point, how many neighbors do you have as a function of distance, and the power that you get is the dimensionality. So you can take that formula, invert it, and then the dimensionality is just the logarithmic derivative of the number of neighbors as a function of distance r. So if I take this spiral example here, where I zoom in really close, if I zoom in really close, I just see 1 point, and the number of neighbors doesn't change as a function of distance. This is like our socially distanced, 2 meters apart in COVID times situation, where the effective dimensionality at that scale is 0. If I now zoom out, I see that my points are arranged more like a plane, so I'd get an effective dimensionality of 2. I zoom further out, and then I realize that my points are aligned in a line, so my dimensionality is 1. And then if I zoom furthest out, then I see that I'm again filling out a space, so my dimensionality is 2. And eventually when I zoom furthest out, I'll find that my dimensionality is 0 again, because my number of neighbors is no longer changing. We can do the exact same thing now applied to jets, and trying to understand a feature from fundamental physics of what is the emergent dimensionality of the spray of particles called jets. And Patrick, Eric, and myself, along with Praksha Nayak and Radha Masandria, we did this using public data from the CMS experiment. And what you find is this fascinating scale-dependent dimensionality for jets coming from the strong force. So at short distances here, or at high energy scales, a jet just corresponds to a single quark or gluon. A single quark or gluon is basically a dimension 0 object, it's just a point. So at high energies, we see that we just get 0 for my effective dimensionality. But then as I go down in scale, I can watch the parton shower develop, and I see that my dimensionality increases, and it's fascinating. I have an effective dimensionality that, depending on exactly what the scale is something like 2, 3, 4, or 5. And this tells you something about the structure of the strong force. This is kind of like a machine learned version of trying to understand something that a quantum field theorist would call an anomalous dimension. And it turns out that this geometric language is very, very powerful. And I don't have time to say more about it in this talk today, but it turns out that 6 decades of collider physics can actually be translated into this new geometric language. Infrared and collinear safety, and this energy flow concept turns out to be very natural in this geometric structure. And then various observables, jet substructure techniques, even pilot mitigation techniques turn out to have a nice translation. And I'd be happy to tell you more about that if you're interested. So, but just to kind of summarize here, can we leverage unsupervised machine learning for high energy physics? And the answer is yes. And this energy mover's distance gives us a chance to do geometric strategies for data analysis in collider physics. And there's been actually some interesting developments there about trying to, for example, make these techniques computationally efficient such that we can actually deploy those on data from the LHC and also for future colliders. So to summarize the talk today, I told you some examples from my research on artificial intelligence and fundamental physics, about encoding theoretical structures directly into neural network architectures, on defining strategies directly on physical quantities and leveraging unsupervised machine learning. And in each of these examples, physics insights were essential for the development of these tools. And then to just advertise one more time, this Institute for Artificial Intelligence and Fundamental Interactions, my colleagues and I are exploring cases where we have both very rich data sets and we have rich physics principles. So for example, the rich data sets coming from gravitational wave detectors like LIGO, combined with numerical relativity techniques. This is a very rich data set to explore. I told you about work in lattice gauge theory and understanding nuclear physics. Dark matter, this is a case where we'd like to understand the distribution of dark matter in the universe, and we can take advantage of various machine learning techniques for that. Particle colliders, neutrino detection, these are cases where machine learning has already proven to be very valuable for data analysis. And even situations like mathematical physics, where questions in string theory about geometries you can start to tackle using machine learning techniques. And the thing that I want to just end with, again, is trying to develop machine learning that's not black box machine learning, but rather trying to take machine learning that incorporates first principles, best practices, and domain knowledge from fundamental physics. And hopefully in this talk, I've given you a flavor about how we can do that, and happy to take more questions from you about how this might apply to your research program. Thanks very much.
Thank you. Thank you for the excellent talk. Let me see if you have some questions here. I don't see any questions on the panel or the Q&A panel. I have my question. In principle, I'm always being, kind of skeptical about this whole machine learning thing because of the black box thing. It's really something that you don't have much control on the the internal machinery, and so I just want to know your opinion about that.
Yeah, so I think the first thing to realize is that we actually do have control over the internal machinery, and this energy flow networks is an example of that. So we put our control into this structure. Of course, we don't have control over the neural networks themselves, but even there, we're starting to understand better how these neural networks operate. And one interesting thing that's starting to emerge is that neural networks seem to behave more like statistical physics systems. That is, as we make these neural networks more and more powerful and have more and more parameters, it's almost like you're going into a statistical physics regime, where as you increase the number of parameters, actually things start to get simple again. And you should be really thinking about, like an ideal gas law, where, an ideal gas is very complicated in terms of the number of degrees of freedom, but they turn out to be relatively simply characterized. And so there's some interesting theoretical work about using quantum field theory and effective field theory techniques to understand, in the limit that you make these neural networks bigger and bigger and bigger, how do they behave? That's an interesting way of trying to wrestle with the fact that, yes, the internals are not understood, but that's also true for condensed matter physics, where the internals aren't necessarily understood, but nevertheless, you can understand the emergent properties of those systems. And it may be that neural networks would be better described in terms of an effective field theory or an emergent property language, which again restores some of our confidence in how they operate. But yeah, my skepticism came from that same place. And I guess the thing that I would say is, we can define the problems that we want to solve, and ideally you can even verify that the solutions that you're getting are sensible. And a big thing that's happening in the field is uncertainty quantification, where you don't just train one neural network, you actually train either an ensemble or you train something like a Bayesian neural network, such that at the same time you get both an answer but also uncertainties about what the machine learning output is. And that's also a direction that makes physicists feel more comfortable.
That's very interesting. I haven't thought about this connection. But, thank you very much. Let's see. We have a question here. So, okay, so the question is for Shivan. He wanted to ask you. I want to ask, how can we take a two-dimensional, a dimension 2, when taking microscopic part, and when seeing as a whole? Well.
So I'm
understand.
not sure. I'm not sure I understand the question, but let me see if I can just show a picture. So so this is in my backup slides. So this space that you get from using this energy movers distance is in general high dimensional. In fact, fractal dimensional, more than fractal dimensional. It changes as a function of scale. But nevertheless, it is possible to project it onto 2 dimensions and expose some of the microscopic properties of the theory. So that space that I told you about before that had this fractal dimensionality or this scale-dependent dimensionality, you can try to make a 2-dimensional picture of it. And shown in gray here are 30,000 jets, but 30,000 jets where I'm ranging the pairwise distances on the slide here in order to make it look as 2-dimensional as possible, basically a projection down to 2D. And then I've sprinkled on top of it 25 example jets. You can see what the phase-space predictions look like. And what's really exciting is that the way that this machine learning technique has arranged the information, I'm trying to project it down to 2D, indeed corresponds to the microscopic physics that we know from the Altarelli-Parisi splitting function, that one direction is the opening angle direction and the other direction is the energy sharing direction, which are the 2 dominant microphysical degrees of freedom that define the substructure of jets. So it does appear that even when you do these projections down to low dimensions, that you capture the dominant features. Of course, what you'd like to do is you'd like to actually expose the full high dimensional space, which unfortunately on a slide is hard to plot. But it is possible to take 2-dimensional projections and still get something that's sensible. So I'm not sure if that was the question, but that's hopefully that's helpful.
Yeah, I hope so. So anyway, that was a very interesting explanation. Also, it was curious about this, about how can you project in lower dimensions. But anyway, let's see. Well, I have another question from Rodrigo. Could we infer new physical principles from machine learning results, such as new symmetries, for example?
Yeah, so absolutely. And there's an interesting question that there's some literature about how do you discover new symmetries in your data set. And so I'm actually working on this myself, and I can tell you what the first thing that we learned is that the definition of a symmetry itself, if you're trying to teach a computer what a symmetry is actually quite delicate. So let's say I have a symmetry not of an object, but a symmetry of a probability distribution. Okay, so we talk about symmetries, for example, of cross sections. A cross section could have a parity symmetry, or a cross section could have a rotational symmetry to it. And what it turns out, though, is that cross sections are basically probabilities, and probabilities. Any probability distribution can be mapped to any other probability distribution. And in fact, that's the basis for a technique in machine learning called normalizing flows. And so it actually is quite subtle to define even what a symmetry means when you're talking about symmetries of cross sections. And we've had to think very deeply about, if I'm trying to tell a computer to find a symmetry, what does that even correspond to? Because again, every probability distribution can be mapped to every other probability distribution up to a Jacobian factor. So yes, there are techniques to learn symmetries. We're working on examples of that. And the challenge is coming up with what's the problem that you want to optimize, whose answer is, hey, here's the symmetry. And this is something that is an active area of research, and I can point you to the literature if you send me an email for some of the papers that are already going on in the field in that area.
Great, thanks. Harvey, you have your question?
Yes, hi, Jesse. So I was struck by both the beauty of your examples, but also the limited scope. And maybe that's just a question of the time that you had. When looking at structures, there are interesting structures which have a time ordering to them. And so I didn't see among the examples where I could see building multi-layered structures which, for example, use time or other parameters as the independent variables. For example, there was recent work that tried to get at the masses which have decayed in the jet formation. Is there information and representations about those things?
Good. So you're right. I didn't talk about anything happening in the time domain. And in fact, it's kind of interesting about the extent to which kind of timing information is relevant or not. So for an ensemble of collisions, time doesn't matter because each collision is independent and identically distributed. So we don't have that time information. But for the generative process of going from the collision through quarks and gluons to composite hadrons to decay, of course, there's absolutely time information. And one exciting development has been the construction of neural network parton showers, where you have a notion of time evolution through the parton shower and kind of building generative models that include that time dimension. Yes, apologies that my examples were limited to just examples from my research. And do I have a backup slide? I don't know if I might have taken it out, about these kind of generative models for collider physics, which in some sense are the more exciting developments, where you'll be able to generate synthetic data sets that both have the training features of having been trained on real data, but then also the symmetry principles built in, such that you can actually extrapolate those trained models outside of their training domain. At least that's the hope that one gets when fusing together the kind of first principles aspect plus the training aspect.
Okay, thank you. We have another question here from Rogerio. Can the geometric strategies identify, for instance, a boosted Higgs decay from the QCD background? How does it compare to the jack structure techniques?
Okay, good. So these geometric strategies are interesting in a couple of ways. So one is that these geometric strategies turn out to be identical to certain jet substructure techniques. So for example, work that I did on n-sub-jettiness a decade ago turns out to be identical to a particular geometric construction. So one can translate existing jet substructure variables into this language. I don't have slides on it here, but for boosted object identification, there's been some interesting jet classification work by the group at UC Santa Barbara, where they've been doing both computational speedups, but also jet classification, including boosted Higgs. And what you do here is that once you have a geometric space, you can now say, hey, in that geometric space, am I closer to the background or am I closer to the signal? And what you find is that those techniques perform very well, but they don't perform quite as well as supervised machine learning strategies. And this is the trade-off one has between supervised and unsupervised strategies. With supervised strategies, you always get the optimal performance, assuming that you have trustable training data. Unsupervised strategies are more general. And so one has to have this trade-off between generality and on performance. And certainly these unsupervised strategies do reasonably well, but not as well as you would get from, again, the unsupervised approach, from the supervised approach, rather.
Okay, thank you. Javier, you still have another question?
Yes, on this last comment, I was struck by the fact that if you look at the work, for example, of the particle flow group in CMS, there was part of the work showed that when you impose your knowledge in a way you think is very sensible, it often is getting in the way. And that seemed to be a particularly interesting aspect when there are aspects which you don't really understand, but if you impose your knowledge, you actually impede those aspects. And what do you have to say about that? And where do you think that will go in the future?
Good. So in general, if you impose prior knowledge, so for example, if you impose something like this energy flow network structure, where you say, I want to have a learning structure that enforces a particular form, that enforcing of that form gives you naively worse performance than you would if you let the network be completely general. And one has to then have a trade-off, again, between performance and interpretability. And one of the questions you have to answer is, to what extent am I willing to get naively better performance, but one, for example, that might be subject to larger uncertainties. So, for example, you can relax this energy flow and energy weighting. And what we find in examples that we've done is that you can get better performance, but at the expense of less stability in the training and larger uncertainties downstream. And so it's an interesting trade-off, one to explore. And I think that there's value in doing both. And there's value both in imposing structures as well as value in letting those structures loosen. And it's also interesting to think about knobs that you can turn where you could smoothly interpolate between having that symmetry and having the absence of that symmetry as part of one's overall training paradigm.
Okay, thank you. Well, we still have one question here since we're ahead of time. Rogerio asked also, can you give a physical meaning to the MVA variables in the neural network analysis, trying to discriminate the beyond standard model signals from background?
Good. So it goes back to this likelihood ratio trick. So what are, if I'm doing a multivariate analysis and I have a neural network that's giving me some output, what does that output mean? What that output is the neural network's best guess for the variables that define the contours of equal likelihood ratio. So if you have a neural network that's trained using, let's say a standard, either a mean squared error loss or a binary cross entropy loss, then the variable that's learned is something that's monotonically related to the likelihood ratio. And this also plays in an interesting way with interpretability. If you think that your likelihood ratio is some nice physical object that is itself interpretable, then good for you. Your neural network is going to learn something that's easy to interpret. But if you think that this likelihood ratio is some very complicated object, then a good neural network will actually learn a very complicated object. So one of the challenges in trying to interpret neural networks is that if the problem is intrinsically difficult, then the variables that are learned are going to be just intrinsically complicated. And that's not a problem of the machine and it's not being interpretable. That's a problem of the fact that the problem itself is difficult. And so that's another trade-off that one has to wrestle with, which is that the optimal solution for a difficult problem is itself complex. And sometimes you might want to trade off optimality, again, for more interpretability or easier to calibrate or something like that. So there's a trade-off that one could explore. And people are exploring, for example, in the context of symbolic regression, where one tries to learn something and then uses a symbolic tool to try to find a good approximation to that answer that nevertheless captures most of the discrimination power.
Okay, thank you. Sorry, Rogerio, you have to ask this question later. He has another question, but since we have already Heather here waiting for the talk, I'm just gonna give you. Rogerio can talk to you privately. Okay, thank you. Thank you very much. Yeah. So for the very excellent talk, and so we now can pass to Heather. Okay, you're there, right? So let me remind you guys again that you should ask the questions from the Q&A, unless you have a microphone, of course. So let me just give a brief introduction of our next speaker, Heather Gray. So she attended to the University of Cape Town, South Africa, in the bachelor degree there in 2005, and then a master degree in physics. She then attended to the Caltech, California Institute of Technology, and obtained a PhD in 2001. She then worked at CERN as a research fellow from 2011 to 2017, and moved to Lawrence Berkeley, LBNL, as a divisional fellow in 2017. From there, she joined the UC, University of California, Berkeley, as a faculty and assistant professor in 2019. And she recently, 2018, she received the UPAP C11 Young Scientist Prize. So without further delay, thank you, Heather, for being with us, and the floor is yours.
Great, thank you very much for the introduction. I'm really happy to be giving this talk. Of course, I'd be much happier to actually be there in person. So what I'm going to be telling you a bit about is a perspective from my side about the evolution of software and computing for high energy physics. So I'd like to sort of start by sort of setting the scene we're trying to think about, the changing software world. And I'm trying to sort of remind us a bit of how this might be linked to climate change, which has certainly been something in the
Heather, we're missing your sound.
Your microphone, please.
data detectors. We have a problem with my computer. Hopefully you can still hear me.
Yeah, right now we can hear you.
Yeah, something weird happened. Sorry. So back to telling you about our field. So we have increasingly sophisticated detectors, higher data rates. We have increased event data volume. We also have increasing demands for physics precision. And at the same time, especially given that we haven't yet found any new physics, we're increasingly interested in exploring unconventional signatures. At the same time, there's a lot going on around us. There's really things like the changing hardware landscape, what Jesse's just been telling you about, all these exciting things that have been going on in machine learning, all these developments in data science, the development of open source software, progress in industry, and of course, unfortunately for all of us as well, funding constraints. And so that's kind of what my talk is about. I'm trying to sort of talk about how things are and perhaps will be changing, and also how these various factors are impacting us and perhaps can impact us in the future. So looking at the internal side, this is sort of just a brief little sketch of the next decade in nuclear and high energy physics. And so you can have a look at the timeline, which goes from 2021 to 2031. Of course, there is the high luminosity LHC and all the various associated upgrades. Of course, for some of the experiments, those like ALICE and LHCb, is actually now where the upgrade is happening, and really for run 3, where things are going to be really quite different. For ATLAS and CMS, on the other hand, the upgrades will be coming somewhere around 2027, and perhaps even a further upgrade for LHCb. Other experiments, there's SPNIX, which will start data taking. There's Bell 2, which has begun data taking, is still really ramping up in terms of luminosity. There's JUNO in the US, which should come sometime near the end of the decade. And looking even further forward, there would be the proposed electron-ion collider somewhere in the following decade. And so what you can see here is that in all these cases, there are many new and exciting things happening, but they're also significantly more demanding than they were before. So now let's talk a bit about those external factors and influences. And I'd like to start with the evolving hardware landscape. This is a slide I stole from Graham Stewart because I think it's great. And it's basically trying to summarize how things have changed from the good old days where we had CPU, memory, spinning disks, and tape, to what we have today in this sort of big blue triangle where we have CPU, we have all these various different types of memory, caches, etc. We also have on the side here, sort of sideways triangle, things like GPUs, FPGAs, device memory, device bus and network. And then this one I added myself is, things like disruptive technologies, things like quantum computing. And I would say that this has already had and will be having a large impact on our field. In particular, if you think about these accelerators, they're really inhomogeneous. They, in addition to the GPUs, FPGAs, you also have things like TPUs, IPUs, and they come from a wide range of vendors like NVIDIA, AMD, Intel, and each of those vendors tends to have their own languages that you need to use to be able to program on these accelerators. From a head perspective, we'd also think, if we're going to use these, we'd have to think how we might actually integrate these into the grid. Now, talking a bit about data science, there's really been a recent boom in data science and machine learning. And Python is really the language of choice for data science applications. There is a huge community which has developed well-documented tools, things like NumPy, Matplotlib, etc. On the other hand, previously what we've been doing is we've been using our own designed purpose and custom tools, most notably, of course, Root. And a plot I have on the bottom left here that I think is quite interesting. This is actually showing, if you sort of look through the Git repositories of people who actually clone the CMS repository, what is the language they use in their own private repositories? So you're just asking, what are the languages people are using for their own development? And what you can notice here is that over time, the usage of C++ has been slowly decreasing, and the usage of Python, and indeed Jupyter notebooks, has really been increasing a lot, especially from, say, 2017 onwards. On the right, this is actually a similar message coming from the EIC software survey, where you notice that 76% of people use root, but then after that, about 30% of them are indeed also using Python. And so this is something quite interesting because it's really the user community that seems to be increasingly choosing to use Python. It's also something that's used extensively, for example, in Bell too. On the other hand, machine learning has been explored in HEP since the early 90s. Classification is used extensively in analysis. And more recently, machine learning has been started to be used more and more in things like simulation and reconstruction. Of course, this was something that Jesse's just been telling you about. And in both of these, there's also a really strong influence from industry, where all these tools are increasingly being used by various different companies. Now, I'm not sure I should really be calling open source software external, because indeed many people in our field have always been passionate about open source software. The one thing that has been evolving is that first our software, then our data, and finally even the livelihoods of the LHC experiments have become open. I will do a caveat. It can be pretty challenging to try and use this data or software if you aren't a collaboration member with access to experts. And I have a quote here from the recent European strategy update, where they suggested that we should really vigorously pursue common coordinated R&D efforts and to develop software that exploits the recent advances in information technology and data science. If you look sort of quite broadly, one of those kind of two complementary and overlapping strategies are developing common software projects. And so these are really tools that might be developed by one set of people and used more extensively, and larger software institutes, which may group together various different projects. And I have a number of them that I've put down below there. Probably I've missed a few, if so, I definitely apologize. But it's definitely a way that things in the computing and software domain have been evolving over recent years. Of course, this can be quite challenging to think about how one might maintain the long-term funding and support for such projects, particularly after something has already been developed. And now what I want to do is sort of step through a typical event processing chain that could be used at the LHC and discuss the impact of these various different internal and external factors on the event processing chain. And so we'll start here with trigger, which is the first thing that would really see the data that comes out of our detectors. And the main challenge for triggers right now is the fact that the readout rates of the various different experiments at the LHC are getting increased dramatically. LHCb is going up to 30 megahertz, ALICE up to 50 kilohertz, Atlas and CMS will, for High-Lumi LHC, go up to 10 or 7.5 kilohertz, respectively. The other interesting thing is that in their Run 3 upgrades, both ALICE and LHCb have really moved towards fully software triggers. And so they're really moving away from these dedicated hardware ones and exploiting the fact that you can actually use software to be able to decide which of the events we need to keep. And so these are two little sketches, one for ALICE at the top here, one for LHC at the bottom, where you can see the various different steps that actually happen in the chain. The other interesting feature, which kind of comes along for free once you think about moving towards software triggers, is to really be able to do full reconstruction within the trigger chain. And that means it really opens up the potential to be able to do many more things with the data far earlier on. There were early studies from ALICE where they first tried exploring GPUs, and they have used them for doing tracking in the time projection chamber since 2012. And for Run 3, they are really expanding this to be able to perform tracking for additional detectors. In CMS, they have a project which is called Patatrack, which has developed pixel tracking and vertexing algorithms to run on GPUs. And what we're seeing, if you sort of look at this all collectively, is it's not only superior technical performance. If you see on the right there, that's actually a plot showing the tracking efficiency where you can compare Patatrack in the blue or the red to the actual CMS offline tracking from 2018, and you can see that the efficiency is higher. But then this little table right at the bottom of my slide, that actually shows the throughput. And so you can see that you also have both equal or better physics performance and superior technical performance. So for CMS, for example, this is really anticipated to be used as part of the HLT during run 3. And so this is one of the moves that you can see many experiments thinking about using GPUs for tracking. Now for the trigger, for LHCB's HLT1, this is actually, as I mentioned, a fully software trigger that performs partial event reconstruction, in particular tracking, with the Allen framework using GPUs. And on the right, you can actually see a plot comparing the Allen throughput for various different GPUs. And you can see how high it can actually become in terms of the rate. And in general, they're actually able to process events at 30 megahertz on less than 500 GPUs, and at the same time to achieve better physics performance than the TDR. And this really reduces the rate from 40 terabits per second down to 1 to 2 terabits per second. Another example from NA62 is on the right. They actually use GPUs in their trigger, relying on an FPGA-based interface card to directly transfer data between the CPU and the GPU. This is called NANET. And again, what we're seeing here is really superior performance on the GPUs compared to the CPUs. Now moving on to the simulation side of things, and we'll talk a little bit about generation. There are really a wide range of generators that are used in nuclear and particle physics, things like Pythia, Magrath, Powhig, Schiffer-Herwig, Beagle, HiJane. In general, these generators are largely developed and maintained by theorists. However, of course, we have increasing precision needs. For example, if one looks into how we will do precision Higgs at the high luminosity LHC, it's really going to be dominated by theory errors. More generally, NLO generation is becoming used more and more extensively. This can require significant resources, particularly for those generators that rely on negative event weights to be able to perform accurate simulations. One of the new ideas there's been sort of some discussion about sharing events, for example, between Atlas and CMS. One thing I want to draw your attention to is this little plot at the bottom. This is one of the foreseen models for Atlas for high Lumi LHC. And you can see here the various different components that we'll be using the CPU for. And the one that corresponds to the generators here, that's that big chunk in purple, where you can see that it's foreseen to be a really significant amount of the CPU that we will use. Now, there's been ongoing work into re-optimize generators and to also port generators to GPUs. For example, with the rearrangement of the Sherpa program flow in regards to the weight variations, they found that it could be either 28 times faster or 1.4 times faster, depending if it was run with or without all the different systematic uncertainties that one needs for the generators. Other improvements that they made, for example, was adding parton shower clustering that got a factor of 4, changing the math library, and then doing QCD virtual corrections using MCFM. Then on the right here at the bottom, this is actually a plot from a design study for a matrix element generator using GPUs. It's still really a work in progress. At the moment, what it can do is to really calculate the all-gluon amplitudes. Now, moving on to simulation. Simulation is really expected to dominate CPU usage at the LHC for run 3. For example, for LHCb, it's foreseen to be something like 90% of their CPU. And for the other 3, it's about 45%. And similar for other experiments, you can see in the various different plots on the right. Now, of course, our gold standard for simulation is JN4. And even when looking at JN4, we know that we need better precision for high luminosity LHC and also other future experiments. On the other hand, given the fact that our data sets are going to be increasing dramatically, to be able to really make as many simulated events as we need, we know that we're going to need to rely on increasing amounts of fast simulation. Now, there are a number of different techniques. First of all, you can make your full simulation go faster. Techniques here include things like Russian roulette, adding in libraries, one of them is VecGeom. And as an example, if you look at the tuned version of CMS Giant4, this is something like a factor of 4 to 6 times faster than the baseline. So you can get really significant speed ups. Other techniques, and they've got various different names. For LCB, there's things like redecay, where this is the plot on the right, where you can actually really take one signal event, you can redo the decay, and keep the rest of the event the same, and thereby saving yourself CPU. Also called embedding, pile-up overlay, pre-mixing. And overall, the idea is to keep some piece of the underlying event and to be able to simulate new signal, because indeed it's really simulating the underlying event and also the pile-up that really requires huge amounts of resources. For certain specialized analyses, you could simulate a single subdetector, for example, a tracking detector. You can also try to parameterize the simulation using things like shower libraries. There are also analysis-specific simulation, ideas about doing end-to-end simulation, parametric simulation, where you just try to do the efficiencies as opposed to really getting events. Particle gun, we just have a single particle, and also the EA simulation tool, which is called EAST. And just to give you an idea about what the sort of gain can be from these various techniques, there's a plot on the right here from Atlas. And this is the time to simulate. It's a WZ event, it doesn't really matter. And you can compare, notice the log scale, how much time it takes in JHunt in black to the first version with a parameterized calorimeter simulation, about an order of magnitude faster. Or when you actually move to a fast simulation of the full detector, you go almost 2 more orders of magnitude faster. And so there's really dramatic potential here for obtaining speed up. Of course, we're also trying to use machine learning in simulation. And in Atlas, we have a fast calorimeter simulation using generative adversarial networks for selective phase space. In LHCb, they're also using GANs, this time for doing the simulation of the particle identification. And other machine learning simulation techniques include things like variational autoencoders, regression, etc. Of course, we're also trying to do simulation on GPUs. Some examples include development of plugins for the electromagnetic transport on GPUs for JN. And the project's name is called ADEPT. And I have a plot on the right there where you can see some of the results. They're very early performance studies where you can see sort of timing compared to CPU to GPUs. A similar project is Celeritas, which also aims to offload this electromagnetic physics. On the right, they have demonstrated that they have reproduced JHunt, and on the far right, you can actually see that they have really large performance gains. There are also a number of groups currently exploring optics, and that Atlas FastCalGAN that I mentioned, that one was actually trained on GPUs. And for example, it took something like 8 hours on the CERN HD Condor GPUs compared to extremely long times when trying to do the training on CPUs on the grid. Then moving on to reconstruction, which of course we would apply to both data and simulation. Here, the CPU time depends really strongly on the amount of pileup that you have. And it's typically dominated by tracking, which is usually has a combinatorial scaling, which is illustrated on the right. I will point out that this is a plot that's going up to mu of 100, where of course at high Lumi LHC, we might get all the way to b equals 200. And for this reason, there are really many ongoing R&D projects to improve track reconstruction. The other plot that's interesting to call out here is the one from CMS, which shows that they would spend something like 60% of their time in reconstruction when they look ahead to what it would be like at the high luminosity LHC. The first way to attack this problem is really using code optimization and modernization, which have been shown to bring significant CPU gains. Techniques used include things like vectorization, multi-threading, memory architecture, and allocation. And those are 2 examples, one for LHCb on the left, which just shows the throughput as a function of time. As you can see, the various different improvements are made, you can really achieve something like a factor of 4. On the right, there's a plot from Atlas, where they're showing how the amount of time is reduced, 1, by designing a new detector, and 2, by actually optimizing the track reconstruction algorithms. One project targeting this is ACTS, which is an experiment-independent toolkit for particle track reconstruction, implemented in modern C++. ACTS has its origins in the tracking software of the Atlas experiment, but is actually already being currently explored for a number of different experiments. And actually just last week, we put the paper out on the archive describing the design and implementation of ACTS. Now, of course, you can do reconstruction with accelerators. And one of the future challenges are high granularity calorimeters. And indeed, if you look at how to do the clustering, this becomes a significant computational challenge. CMS have developed the highly parallelizable CLUE algorithm. And this is already obtaining speed increases of something like a factor of 50 to 100, or factor of 1.2 to 2, depends if you compare this to a single or 10-threaded CPU. These sketch here is actually illustrating a little bit how this clustering algorithm can work, and you can start from the energy on the left, and you can progress all the way to the right, where you can actually see the different clusters. And in addition, they have been exploring GPU and FPGA clusters as a service for deep learning training and inference. And this is something that has been really explored by a large number of groups. I have some links here of them. And you can see on the right one example, which actually shows the throughput time where you can compare to the nominal algorithm, or when you're running on either 1 or 4 GPUs. Machine learning has been used extensively in reconstruction for flavor tagging. A different example is from June, that you can see on the bottom left, where they find that they get superior performance using convolutional neural nets in order to reconstruct the energy and the direction of the electrons. There has been improved performance shown for a CMS-like detector with particle flow reconstruction using graph neural networks. That's the one where you can see it here in the middle, where you can see the improved physics performance, and on the right, you can actually see the timing performance. And another example is that in Bell 2, they have implemented full event interpretation using multivariate classifiers. Finally, to step on to analysis. Here, unlike what I've been talking about so far, the primary challenge is actually about the amount of disk that you need. And you can see a plot here from CMS showing the total disk required as a function of time, and notice the large jump as we get to high NUMI LHC. Similar plots on the right for Atlas. And it's really the case that the analysis models commonly used in Run 1 and Run 2 really expect users to have direct access to the low-level reconstructed objects. These often run under significant time pressure, and they use machine learning extensively. Something I'm not going to talk about here are distributed analysis tools, where one can use these to be able to really trade the amount of tape you need for the disk instead. Now, if you look over time, there have been many competing factors which have really kept analysis models rather fluid. One, there is the requirement to have flexibility and ease of analysis versus the needs from computing. We seem to move between having tiny formats for specific analyses versus shared formats for multiple analyses. Sometimes we want our software to be framework readable, sometimes we want to be laptop readable, or both. There's also the use of high-level physics analysis objects to make analysis easy versus the flexibility to be able to develop new and innovative techniques. We also need to have stability and consistency. We want to be able to reanalyze old data sets. And there's this tension between the analysis precision versus the amount of disk space that's needed. On the right here, I have two sketches from two recent talks, one showing CMS and one showing Atlas, showing these various different complexities that one needs to think about when going through these different analysis models. Further ones are things like lossy compression. People are thinking, how accurately do we really need to know every single number that we have? Do we really need it to know to that many digits of precision? We're also thinking about moving towards a centralized analysis production. Things like analysis trains, first from B0, now Atlas and Alice, or the Dirac system, which is something used by LHCb. Some paradigm shifts, ones that I've mentioned already, include this Python ecosystem and data science tools for analyses, For example, there's CEPC, which is a project really making these tools easier to use in HEP, and also things like columnar analysis. Sort of paradigm shift is something called declarative programming, which has been used or is being used in both L2, Alice, and there's a tool for it, which is called COFIA. In my last couple slides, I'm going to just talk about something different. And I just want to make a quick call out to quantum computing, because this is a field where we've seen dramatic changes in the hardware. And this slide is just showing some of the recent machines that we have. Some you've probably heard of, things like IBM's latest quantum computer of 65 qubits, Google Sycamore, which is the one with 53 qubits. And this is the one which obtained recently the quantum supremacy. Now, of course, with some new technology there are a lot of people already thinking, how might this be useful for high energy physics? And I don't have time to go through all these examples, but there have been efforts thinking about, are we able to solve theoretical problems that have been hitherto untractable? Could we use quantum computers to really improve track reconstruction? And can we use them to perform analysis using machine learning? And that really brings me to the end. Hope I've tried to show you that HEP software may be facing a rapidly changing world, and it's due to both internal and external factors. However, I think that this can also be viewed as an opportunity, and I've only had a chance to touch on some aspects of the exciting areas of R&D trying to address these different problems. Thank you.
Thank you, Heather. Thank you very much for the excellent talk. First, before we start the question, let me remind all the speakers to please upload their talks to in the Indico page, so that people can look at it later, and maybe give also your email so that you can exchange information and all that.
Sure, I'll do that. I had problems accessing it today, unfortunately.
Yeah, no, that's this thing about the virtual whatever. It's a pain. No, I prefer having presential things that we can. Okay. So I don't see much of any hands raised. Nope. Just one curiosity about the last thing you said about the quantum computing. So is it how I mean, is it really can it really help in some of these areas? I mean, I know of course the quantum computer has been at least the theoretical thing. It's of course with us for a time, but can it really be helpful in real sense?
So I think it's a little bit early to know for sure. And I think one of the main problems, right, is we're actually waiting for a useful quantum computer to be built. And what I mean by useful is one that can be much more general purpose than the quantum computers that have been done today. But the reason why people are doing studies now is to actually try to answer that very question. And I think there are some interesting things. I mean, there's certainly, for example, if you think about lattice QCD, one could easily imagine that there might be potential with the quantum computer to be able to solve problems that we haven't been able to do before. One of the examples I have here, for example, is showing how one might simulate a parton shower, really taking into account correlations. For tracking, there were various algorithms. I did one of them where it's just thinking about trying to solve these problems in a different way. And here, of course, you need a far bigger quantum computer with many more qubits to do something. And then for machine learning, again, this is limited by the number of qubits, but there are already kind of preliminary indications, though it's a bit debated, that it might actually be quicker to be able to train or using a quantum computer than trying to train these same algorithms on other computers.
Okay, thank you. Okay, don't see any hands up or anything. So again, thank you very much for the excellent talk, and I hope we can meet you face to face sometime later.
Thank you.
Okay, so now we should have a break. I guess we can have a break of 5 minutes, right? I'm just gonna grab a cup of coffee there. So
Go ahead.
so Alberto, you can tell some jokes while I'm out. Okay.
I believe that we can go ahead, Jovan.
Yeah, sure. So Professor Javier, are you ready to the talk?
Yes. Should I?
Yeah.
Maybe
share
another
your screen.
minute or so. I need actually.
Okay, that's fine. If you want to take a coffee, go ahead.
Yeah, exactly.
Yeah, unfortunately, I can't give you your mic. How does virtual coffee?
Hello, Jovan. You took the coffee break literally.
Yep, indeed.
I will do the same.
Sure. No. Well, we're kind of ahead of schedule, so that's. Okay, ready? Yeah. Let me just give a quick reminder for people that they should put the question on a Q&A button at the bottom of the the Zoom thing. And also I'm asking all the speakers to please upload their talks and also give some email information so people can exchange information. So just to give you a brief introduction to our speaker, Professor Javier Mauricio Duarte. So Professor Javier graduated as a Bachelor in Science in Physics and Mathematics at MIT in 2010. Received his Master and PhD degree at Caltech in 2017. He was a Letterman Fellow at Fermilab from 2016 to 2019, and currently is Assistant Professor at the University of California, San Diego. He's also a member of CMS Collaboration at CERN, and research interests include machine learning techniques, measure properties of the Higgs boson, and search for beyond standard model with the LHC data. So without further ado, Professor Javier, the floor is yours. Thank you.
Thank you so much for the introduction. Yeah, so as you can see, so my topic today was rather broad, so machine learning for high energy physics. So I'll try to make that actually a little bit more specific and focus on actually applications in experimental high energy physics. And if I'm being honest, I'm actually going to be even more specific and really focus on collider physics, or really on ATLAS and CMS. But I tried to find, cherry pick a few examples that I thought were interesting, that are relatively new, and really span the wide range of ways we're using machine learning, and also focus on applications that are really being used today in the experiments. And so just as a brief intro, so particle physics has been linked to machine learning and neural networks for quite a long time, since at least the 1980s. And you could see some early work from Bruce Denby on neural networks and cellular automata in experimental high energy physics. And in recent years, this use of machine learning has really expanded into new territory, sort of starting with machine learning for jet tagging. So actually classifying different kinds of particle jets, or showers that you see in the colliders, in the detectors, as the different, based on their particle of origin. But also in a very different way, they've also been used to try to speed up our generation or simulation. We're also starting to use them for our reconstruction. So actually not just sort of identifying different kinds of particles, but also telling, figuring out how the detector signatures map to the, which particles, are, really clustering the detector signals in a way. And finally, we're also starting to use these machine learning algorithms in this very specialized way in the trigger, which has these, to actually choose our data. And the trigger has all these different constraints, which mean that we can only really run algorithms that are very fast or small, require, have a really small footprint. So accelerating these algorithms in order to use them in the trigger. And very broadly speaking, we're interested in sort of two different advantages we get from machine learning. So one is to try to really improve our sensitivity to physics, whether that's new physics or standard model, sort of known physics that we want to measure better. And the other big advantage we hope to gain is to improve the computational performance. And of course, the sort of golden thing would be to actually have both of these. And so I'll focus on sort of examples that highlight either one or the other, or potentially both of these aspects. And so again, just a quick summary. So what is machine learning? So machine learning, the way we typically use it in high energy physics, is really deep learning. So like maybe a subset of it, which is the structured use of the use of structured neural networks with many hidden layers as generic functions to approximate the optimal solution for a given task. Luckily, I already had a lot of speakers kind of explain, this stuff, so I can go through this relatively quickly. But why do we use deep neural networks in particle physics in practice? And the short answer is basically they work. They seem to give us good performance gains over our traditional algorithms. One area in which they are often, are used to high effect is when there's lots of data and simulation, which is exactly the case that we're kind of blessed with in particle physics. In recent years, we have these fast ways to train them, lots of software that make it really easy to learn how to use these complex machine learning algorithms, and then also train them with specialized hardware. And finally, as you can see from the previous talks, we can possibly gain new insights theoretically into the way that both machine learning works and fundamental physics works. So to start with, I'll focus on sort of one use case, which is machine learning, sort of one of our classic use cases, which is machine learning for jet tagging. And so one of the big motivations for this is actually to better understand one of the central tenets of the Standard Model, central pieces of the Standard Model, which is the Higgs boson. So as you can kind of see from these two graphics, the Higgs boson really plays a central role in the Standard Model. All particles, interact with it and potentially, gain their mass from the Higgs mechanism, which leads us to the idea that potentially if there's new particles or interactions, the Higgs might be a way to sort of observe them. So we might be able to use this Higgs portal, so to speak, to observe these new physics or interactions. So we're really interested in measuring the properties of the Higgs boson very precisely, because that can give us a window into these kinds of new physics. So how do we actually detect Higgs bosons? One of the ways that we've traditionally detected Higgs bosons is using the decay to 2 photons or 2 Z bosons. And these, as you can see from this pie chart, have a relatively small rate, but our detector signals for these decay channels are very clean. So there's relatively low background for these channels. As you can see, though, there is another channel that has a much larger rate. So this Higgs decaying to 2 bottom quarks, but it's actually much more difficult, not only because bottom quarks leave these complicated jet showers, jets that are messier and harder to measure, but also because there's a huge amount of background. There's basically many ways that the LHC can produce 2 bottom quarks. So there's many more types of background that can that are hard to distinguish from the signal. So to give you kind of like a visual of what this looks like, so here's a putative Higgs boson signal from the CMS detector. And as you can see on the left, there is, this kind of, seemingly clean signal of, these 2 potentially prongs of energy, these 2 bottom quarks inside of this jet, which is this orange cone that, we cluster this energy from the tracks and the calorimeter into this object. But unfortunately, it's hard to distinguish this signal from the background, because there is a background like gluons that can split to 2 bottom quarks that can happen up to 10 to the 7 times more frequently than our signal. So it becomes very challenging to try to distinguish this very rare signal from this this background that occurs at a very high rate. So of course, the natural question is, can machine learning help us to distinguish these 2 cases? And so the way the features we want to use of jets in order to distinguish these things come from the fact that you have these 2 B hadrons inside of a jet. And so B hadrons have this nice property that they have relatively long lifetimes, and they can travel order of millimeters before they decay. And so what that means is we can use the fact that they create these secondary vertices from which these displaced tracks emanate in order to actually distinguish them from jets that only have prompt quarks that decay very promptly. So you actually look for these displaced secondary vertices that have some flight distance between them and the primary vertex or the primary collision interaction. These tracks can also come with like large impact parameters. And often these jets will also have these soft or low energy leptons in them. And then we can also take into account the relative positions of the secondary vertices. So all in all, we have lots of these interesting features that we can take advantage of. We have these secondary vertices, we have the actual tracks, and potentially also the leptons inside of the jet. So how do we represent this complicated object with all these different features? So in deep learning, so far, tailoring the algorithms to the structure and the symmetries of the data has actually led to really outstanding performance for a variety of tasks. So as a classical example, we use convolutional neural networks for images. And that's because these convolutional neural networks sort of scan across the image with some fixed filter, some fixed kernel. And what that means is that we're basically embedding translational invariance into our algorithm and looking for the presence of some image, or trying to classify the image. And this is a natural way to take into account that sort of translational invariance. In addition, we've used recurrent neural networks and more recently transformers for language processing, which again kind of take into account the context around a word and are able to use that to do better for language processing tasks. So what about high energy physics data like jets? So here actually there's a sort of popular embedding of jets into this data structure called a graph, or sometimes called a particle cloud. And what this means is we take each of the particles, let's say the constituents of the jet. In this case, you can see on the left, this cartoon of each of these, let's say, charged particles coming out of the jet are curving in the magnetic field. And so they have some momentum that we measure based on this curvature. And so we can take each one of these particles and embed it as a node in a graph, or as Jesse was saying earlier, you can think of them as elements in a set. So these nodes in the graph then each of them have some vector of features. So in this case, the node features might just be the particle form momentum. So you might just have the pt eta phi and the mass of the different particles. But there's actually an additional kind of structure you can consider, which is the connections between the nodes. So you might say, you might think about the edges as being kind of connections between these nodes. And there are additional features or additional vector of information that you can consider for each of these edges. So a natural one might be the distance in some space. So you might look at the distance in the pseudo-rapidity angle plane, so eta and phi, and that can tell you essentially how close these two are, in terms of the detector geometry. And then finally, we might also consider sort of graph level or global features of the jet. In this case, a classic example would be something like the jet mass. So something where you need information from each of the nodes in order to reconstruct some global feature of this graph. So all of these things can be embedded in sort of this kind of graph or particle cloud representation of the jet. And so how do we then use this data representation? How do we run neural networks on this representation? So this falls under this very broad field of graph neural networks, or sometimes called geometric deep learning, which takes these interesting data structures as input and actually runs some neural network or some machine learning algorithm on them. So again, the way we represent the jet here is a set of nodes with some feature vectors. So these are these xi features. But then there's also coupled with it some adjacency matrix, which tells you which nodes are connected to one another. So this tells you the edge connectivity between these nodes. And there might be some additional edge features as well that may not necessarily be represented on this figure. And then the way that we actually run a neural network on this in order to maintain sort of the permutation and variance, the sort of graph-like structure of it, is we use basically these two steps. One, it might be called the message passing step, which is where neighboring nodes, you basically run some neural network on the information basically between pairs of nodes, and use this information to update the state or update the feature vector of each node to give you some new feature vector, which we sometimes call the latent feature vector of each of the nodes. And then finally, this latent feature vector can then be used for further downstream tasks. So you might try to predict something about different parts of this graph. So for instance, if you're interested in sort of node level predictions, you might be interested in, for example, identifying which particles inside of a jet are pileup. In that case, you might take this latent vector and then apply some other neural network to it to basically classify it as pileup or not, for example. You might also be interested in graph level tasks. So actually looking at the whole, the latent vector of all of the nodes and trying to classify the whole graph as something. So in this case, jet tagging, which I'll get to more in a minute, is a perfect example of this. We want to know whether this whole collection of particles is one kind of jet or another kind of jet, like belongs to Higgs to BB, or actually is something more ordinary like QCD. And then finally, also an interesting task is if we might be interested in sort of the edge level tasks. So a classic example of this is for the tracking problem, we're interested in predicting whether two hits, let's say in a tracker, are connected, basically the connection between these two hits correspond to part of a track, so are a good track segment. So this is related to this classic tracking problem that has been studied in depth with these graph neural networks. So back to sort of our application of these GNNs to jet tagging. In this case, we have basically these kind of two constituent graphs that we can consider for the jets. There's the particles, and then there's these secondary vertices. And we can kind of think of them as two separate input feature input graphs that we can consider either separately or together. So typically, graph neural networks kind of consider homogeneous graphs. So they only look at a graph of one type of particle, type of constituent. So in this case, you might have a graph of particle-particle interactions, and then you might actually also look separately at the graph of vertex-vertex interactions. So these secondary vertices, which have these different features, but could also be really interesting to classify these Higgs to BB jets. And so finally, then the sort of naive way you can combine these things is actually do the message passing, do all of the graph neural network steps separately, and then at the end kind of combine the information into one large summary of the whole jet, and then use again a final kind of neural network classification layer to help you kind of combine this information into one classification problem. This is one way to do it that is kind of classically used in our problems. So one example where this is exactly the approach used is this particle net model, which is used for tagging Higgs to BB jets as well as other kinds of jets in CMS. And the way that it works is basically using this graph neural network architecture, but it also uses a special additional interesting feature, which is these dynamic edge convolutions, which is the fact that the graph is actually not known a priori. You don't need to specify the adjacency matrix for the particles, but actually it's constructed dynamically based on the closeness in some latent space. So this is what these edge conv blocks mean. And so what that means is that the k nearest neighbors are computed in this latent space. So it's not necessarily the nearest neighbors in the real space, but actually in some abstract space that might represent different features that are interesting for the ultimate Higgs to BB tagging test. And what we find with this kind of approach in CMS is that we can identify Higgs to BB jets with very high accuracy. So in this case, we can get a true positive rate of over 50% with a very small false positive rate of less than 0.1% for this architecture. And so that's something that is already being studied and used in a variety of analyses. And actually, we hope to have results soon for these kind of analyses, which I'll hopefully show in the future. So, but going beyond tagging, actually, we can also look at an important property that's used to analyze these Higgs boson jets, which is the invariant mass. So right now, one of the sort of state-of-the-art techniques is to use this soft drop mass, which is this algorithm that basically grooms away the soft and wide angle radiation and as you can see, kind of improves the mass resolution, which is really important to getting sort of the best sensitivity to these kinds of signals. And so natural question is, can we do better than this kind of algorithm with machine learning? And so this is sort of hot off the press, but we have this new training of particle net, which actually uses as a target, instead of the the class of the jet, actually uses a target of the true jet mass, where true jet mass has to be defined rather carefully, but also uses these special training samples, which incorporate both BB decays, CC decays, and then light quark decays with varying X scalar masses. So where X could be like Higgs boson like particle with a mass that varies between 15 and 250 GeV. So then for the target mass, the true mass, we use kind of a mix of scenarios. So if the jet is QCD, obviously the sort of the true quote unquote mass of the particle that originates the shower would basically be zero, very close to zero. But this is kind of a difficult thing for a neural network to learn, just to like identify something as 0. So instead, what we use is the soft drop mass of the generator level particles, because there is some real mass generated in the radiation shower of the particle of the shower. So we use this as the target mass for if the jet is QCD, and then we use the actual pole resonance mass of the Higgs to BB jet or X jet, which again can range between 15 and 250 GeV. So then we minimize this loss function that basically looks at the difference between these two, the target and the predicted mass. And what we find is basically that there's a substantial scale and resolution improvement for example, Higgs to BB jets. So here you can see how the regression improves on the ratio between the reconstructed mass and the target mass for these Higgs to BB jets. And this scale and resolution improvement can actually give us much better sensitivity to rare Higgs boson signals like di-Higgs and VBF and other channels. Okay, so that's sort of probably going over time. So that's one important sort of case where we want to use machine learning to improve our sensitivity to physics. So now I'm going to shift gears a little bit to talk about how we want to use machine learning to actually improve our computational performance. And so one of the things that we expect in the coming years is that the CPU demands at the upgraded LHC will kind of explode to really high proportions, as kind of was talked about in the previous talk. So computing demands are really increasing non-linearly with increasing pileup, which is the consequence of trying to get more data, essentially. And so we need more processing power or smarter and more efficient algorithms in order to keep up with these demands. So one big part of this is the fact that our simulation takes up quite a bit of time in terms of this processing. And one popular way to try to speed this up or to try to replicate this or replace these simulation is using generative adversarial networks, or GANs. And so the way they work, very broadly speaking, is that we train two neural networks in tandem. So one will generate realistic fake data from random noise, and the other will try to discriminate the real data from the fake data. And so we use these two together and train them sort of against each other in order to improve the generator. And then ultimately, we can throw away the discriminator, because what we're really interested in is a generator that can reproduce any data distribution as realistically or with as high fidelity as we want. And of course, this has been used to high effect for things like deep fakes. This is an example from StyleGAN2. So you can visit thispersondoesnotexist.com and see lots of images of people that don't exist and are just generated from this kind of network. So this is being used actually already in experiments like ATLAS. So in this case, the way that it's being used is to try to speed up the JONT4 based ATLAS simulation of the full calorimeter. What is done is basically the calorimeter signals that are here are basically voxelized into essentially images, or 3D images in different bins of this calorimeter, and then a GAN is used, or actually 300 separate GANs are used and trained to parameterize the detector response to photons, electrons, and pions in all different sectors of the detector. And what they find actually ultimately is that there's good agreement between the GAN and JONT4 for both single particle showers and for jets. So actually not just at the single particle level, but they've actually integrated this into the downstream reconstruction and seen good performance at the jet level. So this is kind of I think a really cool example of something already being used in the ATLAS software. So as an alternative to voxelization, so where you actually have to basically make everything into images, or 3D images, we can actually also think about using sort of graph-based architectures to generate jets as sort of particle clouds, to generate these kinds of sort of more abstract variable-sized data representations. And so recently, actually, work done in my group by graduate student Raghav Kansal has shown that you can use this kind of graph-based GAN to successfully generate these jets. So you can see on the left the generator and discriminator architecture, which uses this message passing. And then you can see that the GAN, which is shown here in sort of the dotted, I guess, plum color, the dotted blue color, actually does a really good job at reproducing the real distribution of jets, both the particle level PT, as well as the relative jet mass, which has this interesting bimodal structure, because these are top quark jets that can have different sort of phases depending on if the jets are fully merged or not, as well as more complex substructure-like variables like energy flow polynomials that were described a little bit earlier. So this is kind of an exciting recent development. Okay, so finally, last topic is I'll talk about how we want to use these different kinds of machine learning algorithms in the trigger. So we really need to accelerate them and use them in this very constrained space. And so just as a quick intro, there's different kinds of computing hardware that you can imagine. So there's CPUs that have sort of the greatest flexibility. There's GPUs that we're using a lot for training these algorithms. There's FPGAs that are reprogrammable chips and have this kind of balance between flexibility and efficiency. And then finally, there's ASICs that have sort of the ultimate efficiency, but are not reprogrammable. So this FPGA is kind of an interesting spot that we use for the trigger. And so in our typical LHC event processing, we start with a collision rate of 40 megahertz. A level 1 trigger has to reduce this to of order 750 kilohertz using a fully FPGA stack. Then we have a high-level trigger afterward that is based on CPUs and reduces it by another factor down to 7.5 kilohertz. And then finally, we have our offline processing. So right now, sort of the L1 trigger is the regime of these field programmable gate arrays. So one interesting thing is that in order to program these FPGAs, actually takes a lot of domain knowledge, a lot of like electrical engineering knowledge, because you have to program them in these register transfer level or RTL like code, which is a little bit different from how we're used to writing code in Python or in C++. And then this code is then synthesized down to the gate level or the hardware level to actually give you sort of some function. So in this case, this adder can be synthesized to these actual gates that can then be put on an FPGA. So what if instead we actually just wanted to specify something at a much, much higher level? Let's say we want to say, hey, I want to run this AI model, this machine learning model in my FPGA. Can I just specify that and then get the FPGA, the gates, all the gates out of that? And the answer is that we're developing a tool that's being used extensively throughout the LHC called HLS for ML to actually do just this. So we have this machine learning workflow where you start with a machine learned trained model, and then you can actually convert it through this high-level synthesis to actually an FPGA project that you can run on an FPGA. So to give an example of something that is being done for the upgrade of the level 1 trigger, one big goal that we have one challenge that we have is to try to determine the transverse momentum of muons in the end cap based on the information available in the level 1 trigger. Now, this is a difficult task because there's actually a lot of different types of detector technology that are in the end cap. As you can see, there's like a lot of different, and the geometry is very complex. Moreover, there's a non-uniform magnetic field which actually provides very little bending, and the bending is what you actually need to measure the momentum. There's large background for multiple sources like punch-through hadrons and various others. And so we've need to define a new algorithm, which is called the EMTF++, in order to incorporate these new detectors, improve the efficiency and PT resolution while maintaining the same trigger threshold as the previous algorithm, despite being at higher pileup. So there's a lot of challenges that this algorithm has to overcome. And so the way that we've gone about it is to try to define a neural network that will use these 36 input features, which are based on basically all the possible information that we have from the different stations where the muon might deposit some energy. And so we have information not just about the energy, but also potentially about the angles at which these muon interactions are happening, And so this neural network will basically take these 36 inputs and then regress this muon PT. And what we find is actually a factor of 3 reduction in the trigger rate using this neural network over the previous algorithm. So it's actually a huge gain and moreover, it's actually linear up until a pileup of 300, which is a big important fact because we need to go to, because we're imagining going to very high pileup. And so this algorithm can actually be implemented in the FPGA using HLS for ML. And we find that it basically fits in the level 1 trigger latency. So this is it has a latency of about 280 nanoseconds, or 240 nanoseconds for this algorithm. And the FPGA resource requirements are relatively small. So the whole algorithm, the neural network plus the previous algorithm plus other parts of the algorithm take up less than 30% of the FPGA resources. So to summarize, so modern machine learning is the latest tool in the arsenal of high-energy physics that has a wide range of applications. Jet tagging, including jet tagging, regression, event reconstruction, anomaly detection, trigger data compression, generation simulation. So I only had time really to talk about a few, but we've really only scratched the surface of what's possible in the future with machine learning. And I expect that there'll be lots of improvements in the future, not only for our physics sensitivity, but also in improving how we design our detectors, how we calibrate our detectors, potentially automatically, and also to reduce the time and cost of our analyses, of our big data analyses. And so with the upcoming data at the LHC and beyond, I hope that we'll continue to explore the edge of the unknown in particle physics with this cutting edge machine learning. And if you have any questions, feel free to email me. So thank you.
Thank you very much for the excellent talk, Professor. Let me see. Let's see if we get some questions here. I don't see any hands raised. Let's see. Okay. Your talk was so clear that nobody has any questions.
Great.
Anyway, well, this machine learning, of course, I always had my prejudice against it, because as I said in the head of talk, in the previous talk, this black box thing. So I'm an old-fashioned guy, so but it's okay. I think we're learning that this machine learning. Well, that's anyway.
Yeah, that is an interesting direction of research, though. Explainable machine learning, and it is it is something that I think more people are trying to address now. Is the black box nature of it? Like, what is it really learning, and how? And we're getting more tools to be able to answer those questions.
Mm-hmm. Okay, I have a hand up here from Felipe. Felipe.
Hi, just a quick question for this HLS for ML, this framework for FPGAs. Is there any restrictions or what kind of neural network architecture can we implement on the FPGAs for now?
Yes, yes, it is somewhat restricted in that the automatic workflow has to work. So basically right now, the most well-supported types of architectures are convolutional neural networks and fully connected neural networks. We have some support for recurrent neural networks and graph neural networks, but it's much more limited in the sense of it's more constrained what kinds of networks exactly fit on there. So part of that comes from the tool, like we only have so much person power that can go into making it generic for all architectures. But part of that is actually real constraints from the FPGA, let's say, data flow. So recurrent neural networks, because of the way that the memory kind of, loops, or let's say the data loops, it is actually harder to implement certain architectures in FPGAs. Like you kind of want it to be data flow architectures where you can just like put data through it, once and not have to like sort of continuously save data in different stages.
Okay,
Um,
thank you. I don't see any other hand raised, so thank you very much, Javier, for the excellent talk, and I hope we can meet in person someday in the next month.
And I think Alberto has a question, maybe.
Oh, okay.
Harvey, do you see Anima Kumar?
No, is that a question or what?
No, it's not a question, please.
Oh, Anima is in the room, I guess. She's just has her hand.
Hi, Anima. Anima.
Okay, so
I guess I needed to join as the panelist, I guess. Hello,
yeah,
hi, everyone.
yeah.
Hi.
Okay.
Hi, Anima.
Great. Let me share my screen. Give me 1 second.
Mm-hmm. Sure.
Can you see everything?
Nope.
No?
Nope.
Oh, don't see.
No.
Do you see my screen or no?
No, we cannot see.
Okay.
Did
Oh,
you
yeah, I
press the
did.
share?
Yeah, there is that.
Share. Okay. Now it's coming.
Okay.
Yeah?
It's coming.
Great.
Yeah, we can see your computer screen. Okay. Now
Now it's okay.
Great. Yeah, thank you.
Just let me introduce you. Okay.
Please go ahead. Yeah.
Just as a reminder for people, for every speaker to upload the talks, please, in the Windical page, so we can, have people talk to you and get in contact with you if necessary and if they want a question. So just a brief introduction about our speaker, Dr. Anankumar. So she received a bachelor degree at IIT Madras in 2004 and PhD at Cornell in 2009. She was a postdoctoral researcher at MIT and from 2009 to 2010, and a visiting researcher at the Microsoft Research at New England. Okay. So from she's also have been an assistant professor at University of California, Irvine from 2010 to 2016, and associate professor at the University of California, Irvine, 2016-17, and a principal scientist at Amazon Web Services from 2016-2018. Professor Anima holds a dual position at academia and industry. She's a brand professor at Caltech at CMS department and a director of the machine learning research at NVIDIA. At NVIDIA, she's a leading research group that develops the next generation AI algorithms. And at Caltech, she's the co-director of Dulcet and co-leads of the AI for Science initiative, along with Isong Yu. So without further ado, Professor Anima, please, you have the floor.
Thank you. Thank you for the kind introduction, and it's a pleasure to join all of you virtually, and hope you're, in good health and staying safe. Hopefully, we are seeing the pandemic end, but still not everywhere across the world. So today, I want to talk to you about how AI is revolutionizing the sciences. At Caltech, as was just mentioned, I co-lead the AI for Science initiative, and the goal is to integrate and collaborate across all areas of sciences with AI. How to build new foundations for AI that can serve the needs of different scientific applications. And how do we then make a paradigm shift in the way we do science today? Where can we replace traditional methods with AI, whether it's in simulation or AI-driven experimentation? So there's lots of possibilities there. And today I'll give you just some like examples of recent advances we have made, and how building new foundations of AI can really serve us to solve hard problems in sciences. So indeed, AI is perhaps the most powerful force of our times. In just over the last decade, as an AI researcher, it has been really exciting to see how much this has grown, right? How we saw neural networks come together with the availability of large-scale data sets and compute infrastructure, and how today we are seeing its application in a wide array of domains. And indeed, with the coming of the pandemic, use of AI in healthcare has only accelerated. In fact, in 2020, the most invested area of AI was healthcare. And if you think about healthcare, all the way from discovering new drugs and vaccines to, understanding care, right? How do we look at, admitting someone to the hospital, to caring for them all through their stay, especially amidst COVID, when you want to minimize human contact, how can you use thermal imaging and AI to categorize activity behaviors of patients has taken off. So all these are just some examples of how AI is shaping a lot of the applications, and it's really path-breaking in healthcare today. So indeed, the way AI came about over the last decade is what I call this trinity of data, algorithms, and compute infrastructure coming together. Now, with the creation of ImageNet, we began to have large-scale label data sets, right? And this was made available to all researchers. And that's something missing in some of the scientific domains. Whereas in some of the other sciences, there is way too much data. If you think about astronomy, the scale of data is really high. On the other hand, if you think about drug experiments, human trials, there is so little data, right? So we need to be able to manage having too little or too much data, and we need algorithms to be able to handle that. But the deep learning revolution has relied on large-scale label data sets. That's been one of the primary catalysts to even getting this revolution started. And the other important facets that many people may not realize immediately is, of course, the compute infrastructure. Without GPUs, we would not have had the ability to train these large-scale models, and we wouldn't have the ability to learn features directly from data like what neural networks do. So this confluence is really important coming together. And when we come to scientific applications at the same time, HPC has grown by orders of magnitude, or at least one order of magnitude over the last decade, in terms of the speed of various standard programs you see here on the left, or the scale of simulations being done, right? And AI is certainly now part of HPC, right? So when you look at Summit and all the supercomputers, we think about now the scale of AI computations. So that can be a much lower precision than the standard FP 64 or 32 bits. That's usually most of the time 64 in the traditional sciences. And I guess that's already one big advantage. If you can do it with lower precision, and you can get a lot more intensity because of the lower precision, and get bigger models due to that. And so AI and HPCs are coming together in very interesting ways. And in fact, recently, what was announced is the creation of the fastest supercomputer for AI. So when you look at the number of AI flops, it's 20 exaflops. which is mind-boggling, right? So exascale computing was just round the corner just a few years ago, and now we are also accelerating the availability in the latest supercomputers. And what you also see is tight integration also of CPU and GPU together for this hybrid HPC and AI applications. There may be a lot of data movement through the integration of CPU and GPU that you can avoid, and you can be a lot more efficient. And indeed, lots of applications in sciences with this level of computing. So then the question is, how do we build the right kind of AI for such large-scale scientific applications? So one motivating application is, of course, predicting the climate, and in particular climate change over the next decades, and quantifying the uncertainty. For that, what you need is both global model and local model, right? So it's a multi-scale problem. You need to be able to have simulations at this fine scale of clouds, for instance, and then be able to map it to the global measurements, potentially all across the globe. So you want planet scale measurements and predictions. And the climate project at Caltech is one great example of being able to do this both by mapping the local simulations to global measurements and being able to quantify the uncertainty. And so what makes these computations expensive is the enormous scale of simulations you need, right? So you need these fine scale cloud simulations, and you also need to be able to map it to global measurements. So can we speed up with the use of AI such simulations? So this gives us a great motivation amongst many others to study AI methods for solving partial differential equations. Indeed, I guess Stephen Strogatz didn't, he wasn't far off the mark when he said differential equations represent the most powerful tool humanity has ever created. So, if you think about modeling materials or fluids, I just mentioned about cloud simulations. All these require the use of PDEs. And what makes it expensive to solve it numerically is the multi-scale nature, right? So usually there are no analytical solutions, so you have to compute them brute force. The question is, can AI learn the underlying representations better? So if you're now repeatedly computing solutions for the same family of equations, let's say we want to do Navier-Stokes for the whole family, but we may want to vary the initial conditions, we may want to vary the boundary conditions. How do we use the power of AI to speed this up? That was our motivation to study this as a learning problem. So the input is like, the set of equations as well as different initial and boundary conditions. And what the neural network needs to output is the solution. So what we aim to study was the use of solution operator rather than just solution at a specific discretization. Because ultimately, if you have the operator, you can solve it at any point in the domain. And so we wanted our AI to be independent of discretization or grid. And that's when it has truly learned the underlying solution. And so we call this operator learning. And so the main difference is instead of learning a neural network to solve a fixed size input to fixed sized output mapping, that is a finite dimensional mapping, we are aiming to learn an infinite dimensional mapping that maps set of input functions, that is initial and boundary conditions, to set of output, which is the solution. And so how do we do that in a nice way, in a principled way? And so the main building block here is to ask, what is the structure of solution for a linear PDE and then be able to compose it with nonlinearities to express any general operator. So this way we get a universal approximator for any operator. So it's able to fit any operator without being dependent on discretization. So as you see here, the layer of kernel integration is the familiar form for linear PDEs. We have this as an integration with the kernel, and we are now going to have the nonlinearity to express any general PDEs. So the question is, how do we solve these kernel integrations in a scalable way? And this is where we use the Fourier transform. Again, traditional methods also use Fourier transform for solving many families of PDEs. So that was one motivation for us. And then, convolution turns into just multiplication in the Fourier domain. And this nice property also makes it very fast and scalable. And so doing this end-to-end, we can learn good features. And the one motivation to use Fourier transform is also the fact it captures global correlations very well. Whereas if you learn small filters, like in a standard convolutional neural network, you only learn local features. And so that's why it's important to have something that captures global correlations well, and Fourier is a great example of that. And so what we found are promising results where we can be thousands of times faster than traditional methods, while being able to train only on low resolution data. So on the right, you can see it's only low resolution data we train on, and we are directly able to evaluate it at higher resolution. And this is only possible because we can learn this in a resolution-free manner. We can solve Bayesian inverse problems this way in a fast manner. We can also solve hard multi-scale problems like plasticity, right? So how does this material impinge on a surface? And do that much faster because of the speed ups we get, not only with the use of AI, but also of the fact that we can accelerate it on GPUs very effectively. So on the NVIDIA side, we have SimNet, where there is very efficient infrastructure built for solving such problems. And what we have is the ability to have networks for both forward, inverse, and data simulations, and clean APIs, simple APIs to solve all kinds of problems involving PDEs and involving different geometries. So this is also something that's available openly, so you can go check it out. So now for a few other examples I want to quickly give you on how AI can accelerate hard scientific problems. And perhaps one of the hardest problems is to effectively discover new drugs, right? Being able to precisely target a particular disease, while not being toxic in general for the human body. And what makes this very hard is the space of molecules is huge, not order of 10 to the 60. So how do we make the search targeted and fast? And indeed now most of the experiments is done is a very small part of this space. And we're always end up discovering drugs that are very close to known molecules. Because we cannot take bigger gems because most of the space is not going to have drug-like properties. So one project at Caltech and Entos, which is a startup that is spun out of Caltech, has been to ask how we can accurately predict quantum level features in chemistry. So when we look at molecules, if we can predict the ground state energy effectively, then we will be able to predict all kinds of properties, right? Because this is going to the fundamental characterization of the molecule. And the Schrodinger's equation is, if you have it, then you have everything. But of course, the problem is it scales exponentially in the number of atoms. So even for moderate molecules, you wouldn't be able to compute it exactly, even on the world's largest supercomputer. So instead, traditional methods have tried to make all kinds of approximations. And what we see is with our method, we can be orders of magnitude faster, thousands of times faster, but also be able to accurately predict with the use of AI. And what we are able to do is, again, a hybrid kind of approach where we use domain knowledge, we use the property of molecular orbitals, we use the equivariance that we have, the rotational symmetries we have in the molecule. We retain that while giving the flexibility of graph neural networks. So that was one example of how the domain knowledge combines with AI to speed up computations. Another area that we are exploring that is very exciting is new hardware paradigms like quantum, right? So there is a lot of promise that this can revolutionize our ability to compute, but also a lot of challenges. So in the nearer term, what's interesting is the ability to simulate quantum systems at scale effectively. And here, can we use AI to make these simulations faster? And that's one area we're pursuing at NVIDIA. And NVIDIA Q-Quantum makes those primitives easily available at scale and be very fast. So you can see here the ability to simulate tensor networks very effectively. And so TensorLee is a high-level API we are building at NVIDIA to enable such simulations. You can write them seamlessly, and you can use good, powerful primitives for that. So as one example of this, we've been exploring the use of different kinds of tensor models for large-scale simulations and asking how well can they solve global optimization problems. And by using low-rank tensor trained models, even though it has low entanglement, what we find is it can still very effectively solve global optimization problems. I mean, here we see that with 100 qubit, the largest simulation we have is 512 qubits on just a single A100 GPU. So, and get very high accuracy in solving these global optimization problems like max cut. So there is a lot of promise that in the nearer term, there is quantum advantage in such problems, and even low levels of entanglement can really go a long way in solving hard global optimization problems. So just to kind of quickly give you an idea of how can we utilize simulations for AI, right? So far, we've said, let's use AI to speed up simulations, but can simulations also augment AI? And I believe that'll be the case when we look at edge devices, when we look at autonomy. There is not just passive learning, but there's also decision making. And in all these instances, it's very expensive to get real world data. So instead, can we look at simulations and train models in simulations, train adaptive algorithms, use adaptive algorithms to train in simulations? And then how can we transfer that to the real world? And on the hardware side, indeed, we need low power computing to be able to support these edge devices. And NVIDIA Isaac is a platform that can enable such robot learning at scale. Just as one example of this, what we showed was the ability to train this four-legged robot in simulation and be able to do that using a curriculum. So you can train it to first walk slow on a treadmill and eventually increase the speed. And this way, we can have it learn an array of skills effectively. And what we also see is the modularity. The low-level primitives we are not training from scratch. We pre-program it and only train the ability to mix the primitives using a reinforcement learning controller. So in this example, you see when it tries to walk, it learns how to mix these primitives. And with this, it's able to handle even situations like the frictionless surface, which baseline models without learning would not be able to do. And here it hasn't seen that during training, whereas the reinforcement learning-based controller is able to handle even such scenarios. And because of this modularity, we can also transfer that to real-world robot seamlessly. And we can also do it on other variety of tasks, like being able to do all kinds of robot manipulations. And we can do these simulations at scale, whereas in the real world, you wouldn't be able to have those thousands of robots. Yeah, so to conclude, I showed you many examples of success stories for AI for science, looking at what's needed for the domain, right? How can we use inspiration from existing methods? What kind of domain knowledge can we encode as priors into these models? And how do we scale them up? Can we get speed ups over traditional methods? These are aspects we've explored in a number of areas. I showed you the example of being able to solve PDEs with neural operator without having resolution dependence, and also the ability to predict molecular properties. And lastly, I showed you some examples of how simulations can provide synthetic data for training AI models, especially in the realm of robotics and autonomy. Thank you.
Thank you. Thank you very much, Professor Anima, for the excellent talk and really inspiring talk. Let's see, do we have questions, please? So let me remind you that you have to write in the Q&A at the bottom. Oh, Harvey?
Oh, hi, Anima. That was a wonderful talk. In our science program, we're looking forward to very long-term data taking and also development. So I have two questions, maybe difficult. One is, starting in around 2016 or so, there was a revival of thinking about analog computing. And a lot of the things you showed, the outputs, for example, in robotics and behavior of continuous systems, are very good matches to analog replacements for digital electronics. Is that something that you thought about, or NVIDIA has thought about?
Yeah, certainly, Harvey. I think that's a great question. So both at NVIDIA and Caltech, there is a lot of exploration of these questions, right? Are there better hardware paradigms to handle the scale up? And the other is the ability to have low power requirements. And Azita Imami is leading the Sensing to Intelligence effort at Caltech. And through that initiative, right, like thinking about wearable devices, brain-machine interfaces that can work on low power. There's a lot of analog, right, devices there. And one joint project we are pursuing is how to look at the co-design for analog devices, right? Because you have to handle noise, and can you make these models be amenable to that? And certainly on the NVIDIA side as well, there is a lot of research papers we are also publishing in the realm of whether we can have low-powered analog devices, and what kind of digital, like analog to digital conversions do we need, and how can we make that right seamless and low power. So yeah, a lot of challenges there for sure.
So my second question is along a somewhat related line, but a very different perspective. We had some talks about future of computing, but in our field, and I think generally we underappreciate the phase transitions or revolutionary changes that will happen towards the end of this decade, namely the end of CMOS, new electronic and optronic architectures in the nanometer and smaller size domain. And this again is, have you thought about those coming revolutions and kind of, do they have a place in your thinking yet?
Yeah, that's a great point too, because we've been thinking of the current era as end of Moore's law, right? But again, if there can be further advances in CMOS and the ability to kind of keep that revolution going forward, then that opens up our ability to have even more effective larger scale models in small devices. But that is, I think, an open question on, is the Moore's law over, or is it going to continue at least for some time more? I think the question of what is the role of algorithms to further speed up on current hardware, right? We'll have to kind of push more on that, because certainly the Moore's law is slowing down, if not completely stopped. So the ability to have effective parallelism in GPUs, the ability to compute in low precision, right? So all these aspects, I think, become more important.
Okay, thank you very much.
Thank you, Harvey.
Thank you very much, Anima. We have a question here in the Q&A panel from Sandro. He wants to know, how can you inspire young students to participate on this revolution? That's a
Yeah, certainly. I think democratization is been a great aspect of this machine learning revolution, because so much of what we are doing is in the open source, right? Like what you see big companies participate in research, publish papers, open source the code, and NVIDIA has been at the forefront of doing that. So a lot of what everything I mentioned is available in the open source, right? So you can go to NVIDIA containers, you can download, for instance, SimNet, and there are models available for different differential equation families. So I think this is where the ability to learn with online MOOCs, like code examples, have access to pre-trained models. I think that really opens up the ability for young people to easily get started. So check out the NVIDIA containers if you want the code. I think fast.ai has resources for notebooks as open notebooks available. There's also NVIDIA DLI, that is Deep Learning Institute, where there are courses available. So I think some resources if you want to get started.
That's great. Thank you very much. I'd like to thank you for the excellent talk, and also I'd like to extend the thank for all the panelists from this first morning session, and also remind you to put your slides on the Indigo page, so we can have people talking to you, have more. So Alberto?
Yes. Now, first of all, I would like to thank you very much for all of you of this morning talks, turning very happy hours here in science. And I would like to propose to you for this afternoon, start to 14:30, if Carlos Garcia Canal agrees.
Yes, I agree, but the problem is that I have announced to this. Sorry, I have announced at 40 hours here for my students, etc. The talk. I don't know if we can change the timetable now.
Okay, then we start to the 14.
It's a diet. It's a diet lunch,
Yes, yes.
Yeah,
That's right. Okay, okay. Excuse
fine.
us for that. Thank you very much for all. Then we stop to eat something.
yeah. Just grab a sandwich and come back here very quickly.
Sure. Okay, thank you.
Thank you for all.
Okay,
So
thank you,
we
everyone.
stop this morning session. I'll see you at 14 hours.